Imagine a galaxy so bizarre, so mathematically improbable, that every rule we thought we knew about how galaxies form shatters the moment you look at it. It has a perfect golden core of ancient stars floating in the deep black of space. It is wrapped in a flawless, luminous ring of brilliant blue newborn stars, and the two regions are separated by a massive, hauntingly empty void. This is Hoag's object, a cosmic riddle suspended 600 million light-years away in the constellation Serpens, and the deeper that scientists look, the stranger and the more impossible it becomes. From its impossible perfect symmetry to its age-defying contradictory star populations, nothing about this galaxy should exist. Yet there it is, a silent, beautiful anomaly, quietly mocking our most fundamental understanding of the universe. A galaxy in a halo. The first glimpse of Hoag's object. In 1950, Arthur Hoag, an American scientist, was using a telescope at the Palomar Observatory. He was using the 48-inch Schmidt telescope to look at the distant stars. At first, there didn't seem to be anything strange about it. It was just another faint, hazy object among the many thousands of others that filled his photographic plates. After a while, however, he saw something strange on his picture plate, a celestial bullseye. It was a bright, perfectly round ring of light encircling a small, thick, and equally round center. At the time, he thought it might be a planetary nebula. This is the glowing, dying gas ring that a star like our Sun leaves behind. That made a certain amount of sense. A lot of planetary nebulae have beautiful round shapes, but something about this object didn't seem to make sense. This ring was far too big and too bright, and the golden core in the middle looked too much like a close, compact galaxy. Hoag was a careful and meticulous scientist, and he refused to jump to any rash conclusions. Back then, in the mid-20th century, astronomers didn't have our incredible modern space telescopes. They also lacked the high-speed, powerful computers that we have today. To confirm what something was, you had to rely on grainy black and white photographic images. You also needed careful, painstaking measurements of brightness and a great deal of patience. Hoag noted its precise location in the constellation of Serpens. He also recorded its unusual, almost artificial-looking structure, but he simply didn't have the tools that were needed to fully investigate it. The image became a part of his 1950 paper, but he described it cautiously as a ring-shaped galaxy, or possibly a planetary nebula. The mystery and one of the greatest puzzles in modern astronomy was officially born. As the years passed, the photographic plates of Hoag's object became a kind of a quiet curiosity among astronomers. Other galaxies were often messy, chaotic, and beautiful in their imperfection. Spiral galaxies had their uneven, clumpy arms, irregular galaxies were scattered with bright star-forming knots, and elliptical galaxies had their fuzzy, indistinct shapes. But this object, it looked like a perfect painting done with a cosmic compass. The ring was so clean, so sharp, and so symmetric. Some astronomers thought it must be an optical illusion or a defect in the photographic plate. They even considered it might be a strange trick of perspective. It wasn't until the 1960s and 70s that astronomers began to suspect the truth. With the advent of better telescopes and more advanced spectroscopy, they began to see something extraordinary. They suspected that Hoag's object was something that defied all of their existing categories. Measurements of the light from the ring showed it was coming from very distant stars. They were much, much farther away than any known planetary nebula. The redshift of the light revealed it was a true galaxy. This stretching of its wavelengths is caused by the expansion of the universe. It was located about 600 million light-years away from the Earth. That meant that the ring itself was enormous, tens of thousands of light-years across. Planetary nebulae, in comparison, are tiny, just a few light-years wide. Arthur Hoag himself had no idea of the puzzle he had stumbled upon. He had no idea it would go on to fascinate astronomers for decades. He wasn't even searching for unusual galaxies at the time. His research focus at the time was on completely different types of celestial structures. But sometimes science advances not through a planned, systematic search. It advances because someone somewhere notices something odd in the quiet corner of a photograph. Something that just doesn't fit. This was one of those moments. Another thing was clear even from the very early pictures. The space between the bright, luminous ring and the central golden core looked eerily unnaturally empty. Galaxies generally have a smooth, gradual change from the dense center to the thinner outer arms or ring. The stars and the gas clouds tend to fill in the spaces between the two main features. But here in Hoag's object, it looked as if the middle had been completely erased. The image was so clear, so sharp, and so well defined. It didn't match any of the known types of galaxies at the time. Throughout the 1980s and 90s, our view improved. Larger ground-based telescopes and new CCD imaging technology improved the clarity. Hoag's object became a kind of odd, unclassifiable cousin in the galactic classification schemes. It didn't fit as a spiral galaxy. It had no arms, no central bar, and no visible disk. It didn't fit as an elliptical galaxy. The outer ring was far too bright, too blue, and too sharply defined. And it wasn't like the other ring galaxies. Those usually showed the clear, telltale signs of violent recent collisions. They had long, ghostly streams of debris and uneven, clumpy ring shapes. They also had nearby companion galaxies that had caused the disruption. The strangest thing of all was that it looked as if it was completely undisturbed. When you see a ring galaxy, it is usually because two galaxies have crashed into each other. This sends out great expanding waves of gas and stars, making a ring. But Hoag's object didn't have any of the usual scars, the tidal tails or the clouds of scattered stars. Nothing suggested that something like that had happened to it. It was there all the time, wonderful and serene. When the Hubble Space Telescope took its famous picture in 2002, the galaxy was already well known. It was known as a strange and a peculiar object in space. The Hubble picture confirmed its breathtaking, almost artificial-looking shape. It showed a dense, golden, oval-shaped core of old stars. This was surrounded by a nearly perfect, brilliant blue ring of young, hot stars. There was a vast, dark space between them that seemed to have almost no visible stars at all. Even stranger, a smaller, fainter ring galaxy can be seen in the background. It looks a lot like the main one, and it is perfectly framed within the empty gap of that same Hubble picture. This strange, almost impossible coincidence only added to the deep, pervasive mystery of the object. For Arthur Hoag, the discovery was an unexpected and an enduring legacy. He retired from active astronomy long before the full mystery was even recognized, but his name would forever be attached to the object he had found. What had begun as a faint, strange-looking spot on a single photographic plate was now something more. It had become one of the most famous "how is this possible" cases in all of extragalactic astronomy. The perfect ring, a shape that galaxies shouldn't make. Many people think of galaxies as majestic spirals with beautiful sweeping arms, or they imagine big, smooth, glowing ellipses. But the truth is that reality is much messier. Spiral arms often stick together, and they are not always straight. Elliptical galaxies can be uneven or long. It sounds like ring galaxies would be neat and round, but they are not always perfect rings. A lot of the time they are bent, broken, or twisted. They look more like a splash in a pond after a few stones have been added. It's not just a simple ring, which is why Hoag's object is so incredibly strange. Its ring is almost mathematically perfect. It is so orderly, so symmetrical that it looks almost fake. The outer structure of Hoag's object is a smooth, unbroken, continuous loop of bright blue young stars. When astronomers measure its circularity, they find the deviations are so small they are almost negligible. That is practically unheard of in the field of astronomy. The universe is full of the forces that disrupt order. There is gravity from nearby galaxies, the uneven pull of dark matter, and the messy nature of star formation itself. For a galactic ring to remain this precise, it means that something very unusual is at work. Ring galaxies typically form when one galaxy punches directly through another. This sets off great expanding ripples of a star formation in a ring-like shape. The Cartwheel Galaxy is the textbook example of this process. It is a sprawling, uneven wheel with bright knots of young stars scattered all across it. But unlike the cartwheel, the ring of Hoag's object lacks the telltale asymmetries of a recent collision. There are no tidal tails of gas and stars that have been flung out into space. There are no visible distortions, no lopsided regions where the collision was stronger on one side. The width of the ring is also quite interesting because it stays remarkably the same all the way around. In some rings, star-forming areas tend to group together, leaving brighter areas where gas is heavier. But there is a very even width in Hoag's object, as if drawn with a cosmic compass. Astronomers can see that the ring's shape is smooth. This is because the brightness doesn't change much from one side to the other. Not only is this beauty nice to look at, but it is also a scientific pain. Chaos rules the forces that form galaxies. Gravity pulls in strange directions, gas clouds fall apart randomly, and stars tend to form in specific spots. It's like watching a storm build a perfect sand castle. All of those forces are working together to make something this orderly without a clear, obvious guide. Some scientists have wondered if the symmetry could be maintained by a kind of resonance. This would be a stable pattern in the orbital paths of the stars and the gas that naturally locks them into place. It's similar to how the rings of Saturn are kept sharp by the gravitational tugs of its moons. But unlike Saturn, Hoag's object has no obvious shepherds. There are no companion galaxies close enough to be sculpting its beautiful shape. The orientation is another strange thing. From our point of view, the ring is facing almost straight ahead. In other words, we are looking straight down at it with not much of a tilt. That doesn't happen very often. According to statistics, the views of most galaxies we see are skewed, which makes them hard to focus on. Seeing one so well matched is like flipping a coin a dozen times and getting a head every single time. It makes the puzzle even more difficult to solve. Astronomers have used computer modeling to try and figure out the ring's shape. These models have different starting points, such as a collision, a gravitational resonance, or an idea. One idea is that the system could be shaped by a strange ring of dark matter, but the models almost always come up with rings that are a little oval, or they have an uneven shine or are full of dust and debris. All of them are not the same as the perfect circle of Hoag's object. If the perfection were only in an appearance, one might dismiss it as a coincidence. But spectral analysis shows that the motion of its stars also follows a well-ordered pattern. This study of the light coming from different parts of the ring shows unusual uniformity. The orbital velocities are consistent across the entire structure. In other words, the symmetry is not just skin deep, it is built into the very motion of the stars themselves. This consistency opens up some scary options. One reason is that the galaxy has been alone for a very long time. This has allowed its structure to settle down without any outside interruptions. But over millions of years it should have been warped by things inside the galaxy like its own uneven gravity. Another reason is that the ring is pretty new in cosmic terms. It was formed not so long ago, so it hasn't been disrupted yet. But then where is the proof of the event that made it? Some astronomers have even joked half seriously that it looks too perfect, as if it were engineered. Of course, there is no evidence for anything artificial about Hoag's object, but the comment itself reflects just how out of place it feels among the universe's usual chaotic creations. The perfect shape of Hoag's object's ring makes it stand out in the lists of galaxies. It has the kind of structure that makes you stop when looking at pictures of stars. Your mind says that it simply cannot be natural. Still, as far as we know, it is a cosmic puzzle in the form of a perfect, beautiful loop. The golden core, an elliptical heart inside a ring. At the very center of Hoag's object is a thick golden sphere of stars. It looks like a small, compact elliptical galaxy. It seems almost as unlikely as the perfect ring that surrounds it. It is not as important as the bright blue ring, but it is still there. As it turns out, most of the galaxy's visible mass is contained within this dense golden core. Its color shows that the stars inside are very old. They are much older than the stars in the ring around it, and their light is warmer, like that of an old dying person. Elliptical galaxies by their very nature are collections of older stars packed into a rounded shape. They are often formed through ancient, violent mergers. They tend to have very little gas or dust, which means they are not actively making many new stars. Hoag's object's core fits that description almost perfectly, and yet it sits in the very middle of one of the brightest, bluest, and most star-forming rings ever observed. That stark, almost jarring contrast is one of its biggest and most profound oddities. The contrast is between the dead ancient heart and the vibrant, youthful outer ring. Spectroscopic studies show that the stars in the core have a much higher average age than those in the ring. In some cases, they are billions of years older. This suggests that the core existed long before the ring was ever formed. That raises an obvious and a very difficult question. If the ring came later, what process surrounded this old elliptical heart with such a youthful, active structure? The core's structure is unusually smooth. There are no dust lanes winding across it, no clumps of gas, and no irregular patches. In many galaxies, even old elliptical cores show the scars from their past mergers. These scars are faint shells, ripples, or streams of stars that hint at their violent, chaotic history. But here, the golden sphere is pristine. If a collision had created the ring, then why did the core escape without any visible damage? On top of that, the core's light profile doesn't match what would be expected. How its brightness changes from the very center outward is not what we'd expect for a galaxy with that much mass. It is a little more concentrated than it was thought it would be. It's as if something had squeezed it together a very long time ago. There is, however, no sign of recent gravity compression from a close collision. It is possible that the core is what is left of a small elliptical galaxy. This galaxy might have moved in close to a bigger spiral galaxy, causing the ring to form before it lost its outer stars. But that doesn't explain why the effect is so clean, as if it was done by a surgeon. Another idea is that the ring could have been made of gas from a long-lost partner galaxy. This gas would have been pushed into an orbit around the core. If that is the case, the gas would have had to settle into a very stable and even orbit. This is much easier to guess than it is to prove. The golden light of the core also provides a chemical clue. The stars in this region tend to be richer in heavier elements, which astronomers call metallicity. This suggests the core has gone through multiple generations of star formation in the distant past. Earlier stars were enriching the gas that formed the later ones, but those enrichment levels don't match the chemistry of the outer ring. This implies that the two regions didn't share the same star-forming history. It is almost as if they belong to two separate galaxies that have somehow become one. The fact that the heart doesn't rotate might be the most surprising thing about it. It has been seen that the central elliptical moves less quickly than was predicted. Many galaxies, even older ones, have a measurable spin. This is because they still have motion from when they were first formed. When it comes to Hoag's object, the ring around it spins much faster. This difference suggests the two systems may have come from very different places, and now they are stuck together in a way that seems to work well. Astronomers have attempted to model how an old elliptical core could remain so undisturbed. How could it be wrapped by such a perfect ring? Most simulations fail because the same event that creates the ring should also disturb the core. An event like a collision or a gravitational encounter should add visible distortions. That has not happened here. The fact that the golden core is so smooth suggests one of two things. Either the ring was formed through a process that doesn't involve major violence, or any disturbance happened so long ago that the core had time to completely relax back into its original shape. Hoag's object is one of the most beautiful galaxies in the known universe. This is because of the stark, beautiful difference between its two parts. The warm golden sphere shines like a source of old starlight, and the electric blue ring goes around it like a brilliant crown of light. They don't blend together because there is that strange empty gap between them. It is almost as if they are being nice and keeping their own space. Stars without a bridge, the empty gap. What is not there in Hoag's object is one of the most disturbing and puzzling things about it. There is a wide, strangely dark area between the burning golden core and the bright blue ring. It is tens of thousands of light years wide, but there are not many stars in it. Even in galaxies with clear structure divisions, there are usually stars in the space between main features. There might be scattered groups or faint clouds of gas. This place is almost completely empty, like a dark moat separating two heavenly castles. Scientists were surprised by how clean this gap is when they first looked at it in depth. Not only are there not many bright stars, but also not many of the weak older stars. The Hubble Space Telescope's deep pictures showed that this void is not just because the stars are too dim to see. The number of stars here is much smaller than what was predicted. It is almost as if something had swept the area completely clean. In a typical ring galaxy formed by a collision, the gap is filled with turbulent leftovers. Leftovers like streams of stars, clumps of gas, and chaotic debris. The Cartwheel Galaxy, for example, has a busy interior between its core and its outer ring. It has knots of activity that are scattered throughout. Hoag's object, by contrast, looks as if an invisible boundary has been drawn. It seems to be keeping the two regions from ever blending together. It is possible that orbital mechanics keep the gap open. If the gas and stars in the ring are moving in very stable synchronous orbits, they may stay away from the core. This is kind of like the way that the moons of Saturn keep some parts of Saturn's rings clear through their gravity. But in Hoag's object, there is not a clear moon or any other object acting as a guardian. The gap might also have been caused by a big event that cleared the area a very long time ago. A big blast of energy from the core could have blown out the gas. Perhaps this energy came from a giant black hole that was there a very long time ago. This would have stopped stars from forming in the area. Over time, the space would become empty because there would be no gas to make new stars. There is a problem with this theory, though. We do not see much proof that a giant black hole is actively affecting the galaxy right now. There is not a bright, active galactic center, any jets, or any strange X-ray activity. The chemical studies add another layer to the mystery. The few stars detected in the gap do not share the same chemical fingerprints as either the core or the ring. They appear to be remnants from an even earlier time. This suggests that this region might be a kind of fossil zone, the leftovers of a structure that existed before the ring. This raises a provocative question. Was Hoag's object once a completely different type of galaxy? Was it somehow transformed into the strange structure that we see now? The emptiness also creates a gravitational puzzle. The core and the ring exert forces on each other, and you would expect that over millions of years this would cause stars and gas to drift inward or outward. They would slowly fill the void, but the gap remains sharp, as if some stabilizing mechanism is constantly reinforcing the separation. The models attempting to simulate this stability often require finely tuned conditions. These are conditions that seem unlikely to persist naturally for so long. One of the things that makes Hoag's object look so strange is the stark, beautiful gap between them. The golden sphere of old stars doesn't fade slowly into the ring around it. Instead, there is a sharp, almost surgical cutoff. With such clear lines between the galaxies, they appear almost man-made. They look as if they were built instead of evolving naturally over time. Even though no serious expert says that it is fake, the way that it looks is disturbing in how real it is. In a world where chaos is normal, this lack of a connection is a very loud silence. The gap makes it harder for us to figure out how galaxies move matter around change over time and keep their shapes. If the ring and core really have different histories, they were made in different times or from different sources, then the gap could be a sign of their union that will last forever. It would be a place where no one has been able to settle for hundreds of millions of years. Even now, telescopes can't fully resolve what is inside the void. It may contain faint streams of dark matter that are invisible to our instruments. This matter could be holding the region in place without adding any visible light, or it may simply be a gravitational dead zone where star formation has been impossible for eons. Whatever the reason is, this empty bridge is a defining feature of Hoag's object. It is as much a feature as the ring or the core themselves, a mystery in negative space, the mystery of the ring's formation. The bright blue ring around Hoag's object is more than just pretty. It is a puzzle that is wrapped around a galaxy. There are not many rings in space to begin with, and when they do appear, they almost always have a clear history. Most of them are what is left over after something big has happened. For example, a smaller galaxy slamming into the disk of a bigger one, sending out waves of dust and stars. Others are caused by gravity resonances, which have a slow but steady effect. They can shape the paths of stars into repeating designs. Unfortunately, Hoag's object will not fit any of these models. The first idea that experts came up with was the well-known collisional ring situation. This model says that a small neighbor galaxy would have crashed through the main galaxy's core. This would compress the gas and start the formation of stars in a ring. What is wrong with that? There are scars in every collisional ring that we have seen. There is space junk all over the place. The ring is not all the same thickness. And there are signs that the invader galaxy is close by or is already joining. There is none of that in Hoag's object. The ring is a uniform shape and its width is the same all the way around. There is also no clear suspect that is nearby to take the credit. Another idea was the resonance ring model. In spiral galaxies, stars and gas can get trapped in resonances. These are specific orbital patterns caused by the gravity of a central bar structure. These resonances can pile up material into rings over millions of years. But Hoag's object doesn't have a bar or even spiral arms where such resonances usually occur. The core is an elliptical, smooth, rounded, and lacking the disk structure needed to make this mechanism work. Some astronomers wondered if the ring might have been formed by the gradual accretion of gas from the galaxy's surroundings. In this cold accretion model, streams of intergalactic gas could have spiraled in. They would have settled into a rotating disk far from the core where they eventually formed stars. While this could explain the lack of a visible collision, it is still hard to understand something. How would an incoming gas arrange itself into such a perfect uniform ring without forming more irregular structures first? A more unusual idea is that the ring's symmetry could be due to the galaxy's dark matter halo. This is the unseen mass that surrounds all galaxies. The idea is that this halo is particularly smooth and round. If the dark matter is spread out just right, it might guide the gas and stars into a safe path. But it is extremely hard to map dark matter halos. And there is no direct proof that Hoag's object's halo is different in this way. The age difference between the core and the ring also complicates things. Observations show that the core stars are ancient, while the ring stars are much younger. This means that the ring is a later addition to the galaxy's life story, not something formed alongside the core. In a collisional model, the timing would have to be precise. The collision would need to be recent enough for the ring stars to still look young. But it would also need to be long enough ago that the ring could settle into a perfect symmetry. Also, the ring that is moving around adds to the puzzle. Spectroscopic readings show that the stars in the ring orbit in a strangely ordered way. There is not much of a scattering of their speeds. Not only are they moving in the same general direction, but they are also moving in almost similar circles. It's as if someone had put them there on purpose. It is rare for models of ring formation to show such consistency. Usually there is turbulence for millions of years after a creation event, but this ring looks calm and grown up. Some scientists have looked beyond the familiar for explanations. One speculative idea is that Hoag's object might be the product of a gentle merger. A small galaxy would be absorbed so slowly and so evenly that it didn't leave behind the usual chaotic traces. Instead, it contributed its material to the ring in a stable pattern. Another proposes that gravitational waves from some ancient event might have triggered star formation in a perfect shell. This would be around the core, though this remains purely hypothetical. Each theory does answer some questions, but it also brings up new ones. Collisions show how rings work, but they don't show how perfect they are. That is why there is symmetry, but not why there is no bar. Gas accretion can explain why the stars are so young, but not why there are no patterns. And there is still no proof for the dark matter ring idea. This is why the formation of Hoag's object is still one of the biggest puzzles. It's a puzzle in the study of galaxies beyond our own. Some theories are called into question, but not just one. It is almost like the galaxy was made to resist classification. It sits in a quiet part of the universe with a structure that shouldn't be there but clearly is. No evidence of a collision. Astronomers first look for signs of a past crash when they see a galaxy in the shape of a ring. That is because most ring galaxies we know about got their shape from a head-on collision. The usual story is that a smaller galaxy intrudes into a bigger galaxy's disk. This sends out waves of gas and stars outward in the shape of a ring. Over time, these waves cause new bursts of star formation, which makes the outer loop bright. It is a reliable model, one that we have seen happen in many systems. The Cartwheel Galaxy is perhaps the most famous example. Its ring is patchy, uneven, and surrounded by wisps of scattered stars and gas. This is all evidence of a violent past. But when astronomers turned their attention to Hoag's object, something didn't fit. For a supposed collision ring, it is missing every obvious clue. First, there is no visible debris. In a galactic smash-up, gravitational chaos flings material into space. This forms tidal tails, long, faint streams of stars and distorted shapes. Hoag's object has none of these. The space around it is unusually clean. There are no tails, no arcs, and no messy knots of gas drifting away from the ring. The lack of these features suggests there was no collision, or if there was, it happened so long ago that every trace has faded. This contradicts the youth of the ring's blue stars. Second, there is no sign of the culprit. In most ring galaxy systems, the intruder galaxy is either still nearby or is already merging with the core. Hoag's object sits in relative isolation. The nearest significant galaxies are far enough away that they couldn't have been recent impactors, and deep sky surveys haven't uncovered any small stripped-down remnant, nothing that could be the remains of a long-absorbed intruder. Third, the symmetry is wrong, or rather, it is too perfect. Collisions are messy by nature. The intruder almost never strikes dead center, and any slight offset usually makes the resulting ring lopsided, but Hoag's object's ring is almost mathematically circular. If a collision had caused it, it would require an impact so precisely aligned that the odds become almost laughable. It would be like firing an arrow across a football field and hitting the bullseye of a moving target. The velocity data also poses a problem. In known collisional rings, the stars and gas in the ring often have a wide range of speeds. This happens as the system recovers from the shock. Hoag's object's ring, however, shows a surprisingly uniform rotation pattern. It's as if it has been stable for far longer than a fresh collision would allow. That means the ring either settled into a perfect order with unprecedented speed, or it was not formed in the violent way we have assumed. There is another possibility. The crash theory could still be true, but in a very strange way. Some scientists have come up with the idea of a ghost intruder situation. In this case, a very small gas-filled galaxy crashes into the ring and blends in perfectly. The problem is that even a gas-filled invader should leave some visible gravitational marks like changes in the way the stars in the core move. However, Hoag's object's core is surprisingly unaltered. There is also a chance that if there was an impact, it was not between two galaxies. It could have been between Hoag's object and a huge cloud of gas. In theory, this kind of collision could cause rings to form instead of normal starry wreckage. But this brings up a new question. Where is that cloud of gas now? And how did it spread out the stuff so evenly? Observations show that there is not a huge gas reserve floating close. Many scientists are hesitant to put Hoag's object in the same group as the Cartwheel Galaxy. They hesitate because there is no proof of a crash. It looks, it acts, and it lives in a way that are all too different from each other. If the impact model can't explain it, then we either missed something very important, or Hoag's object shows a completely different way that galaxies evolve. A cosmic isolation chamber. What makes Hoag's object unique is not only its perfect ring and its strange core, it's also the fact that it lives in a very empty part of the universe. Galaxies tend to be social. They stick together in groups, pull on each other with gravity, and sometimes crash or join. Even though these interactions are messy, they are what make galaxies change over time. They move gas around, make new stars, and change the shape of structures. On the other hand, Hoag's object looks like it was left alone for a very long time. When astronomers chart its surroundings, they find a startling lack of close neighbors. Hoag's object sits far from any major galaxy cluster. Its nearest significant companions are millions of light years away. They are too distant to exert any strong gravitational influence. The space around it is dominated by an emptiness. It's broken only by the faint, distant galaxies scattered across the background. In galactic terms, it is living in the countryside far from the bustling city centers where galaxies constantly interact. This isolation matters because it removes many of the common triggers for dramatic galactic change. In denser regions, galaxies are constantly disturbed by the tidal forces from their neighbors. Gas streams in and out. Collisions are frequent, and gravitational harassment can warp their shapes. Without such influences, a galaxy's structure can remain stable for billions of years. That might explain how Hoag's object's perfect ring has survived without being pulled apart. There is simply no one nearby to disrupt it. The isolation also creates problems for the standard models of how ring galaxies form. If Hoag's object is so far from other galaxies, then the usual explanations become much less likely. Explanations involving collisions or tidal interaction. There is no obvious partner that could have created the ring through a direct hit or a close pass. Even if such an interaction happened in the distant past, the intruder would have had to escape. It would have had to escape without leaving any visible trace, which is hard to reconcile with galactic dynamics. The lack of changes in the surroundings also makes the youth paradox harder to fix. Since the stars in the ring are not very old, the structure was likely made not too long ago in cosmic time. But if there has not been a nearby galaxy close enough in recent months to set it off, then what caused it? What could have caused such a big burst of star formation in a circle? Some experts think the fact that Hoag's object is in a low-density area may have had a more subtle effect. This area is sometimes called a cosmic void. When there are not many people in these places, intergalactic gas can flow more slowly. It can flow without being stripped or heated by frequent interactions. In theory, that gas could be pushed equally into the galaxy from different directions. It would then settle into a symmetrical circular path, creating the ring. But the details of how such a process works are still mostly guesswork, and the models have not been able to clearly copy it yet. Hoag's object's remoteness may also be the reason that it has remained so pristine in appearance. In busy galaxy clusters, even if a ring forms, it is likely to be distorted within a few 100 million years, distorted by the gravitational pulls of nearby giants. Hoag's object may have had the luxury of evolving in near total peace. This would allow its unusual structure to freeze in place without external interference. Being alone could also explain why its core doesn't seem to be affected at all. The core might stay smooth, dust-free and stable for billions of years if it has no nearby stars to stir things up. It would also need no new stuff to feed on. This would make it a dinosaur relic, a well-preserved piece of a different time in galactic history. It would be ringed by a ring that was formed much later through a process that is still unknown. The quiet place where Hoag's object is found doesn't answer the bigger question of how its ring came to be. The isolation actually makes the problem worse because it takes away the most widespread reason. Imagine you look in a pond and do not see any stones, any sticks, or any fish that are close. You might find a completely round ripple. The event must have been different from anything that could have come from a nearby star system. Astronomers continue to survey the space around Hoag's object. They are looking for faint traces of past interactions, maybe a ghostly stream of stars far beyond the ring, or a barely visible dwarf galaxy. This could be the remains of a long-lost partner. So far, the search has turned up nothing conclusive. The double ring illusion, the background twin. Astronomers and the public were both amazed by the beauty of Hoag's object. This was when the Hubble Space Telescope took its famous high-resolution pictures of it in 2002. An even stranger surprise was tucked inside the outer ring and far in the background of that same frame. It was a smaller, fainter, ring-shaped object. It was quickly called the Hoag's twin, or the smaller Hoag. Right away, it looks like something out of this world. It's as if the universe were repeating itself at two different sizes in the same line of sight. The inner twin is not at all a part of Hoag's object. It is very far away, so far away that the two galaxies will never meet. The only thing that makes them look alike is that they are aligned so perfectly from our point of view. But the chances of this happening are out of this world. The background twin appears through the gap between Hoag's object's golden core and its bright blue ring. That placement makes it look almost staged, like a deliberate design choice in a piece of cosmic art. If the smaller ring were just a few arc seconds in another direction, it might have gone unnoticed. But instead, it sits perfectly framed. It's a smaller echo of the main structure peeking through the emptiness. Because it is so far away, the background twin is much harder to study in detail. Even with Hubble's clarity, it appears as a tiny smudge of light. It is just distinct enough to show a ring-like shape. Spectroscopic measurements are difficult, but early observations suggest it too might be a ring galaxy. Its structure could also be the result of a gravitational lensing or another phenomenon. Without sharper data, its exact nature remains uncertain. Some have suggested that the smaller Hoag might not even be a true ring galaxy. It could be a galaxy seen through a patch of dust or gas that is blocking its center from view. This would create the illusion of a ring, but the brightness distribution seems to favor the idea of a genuine outer structure. If that is the case, it would mean we are witnessing two rare cosmic objects aligned purely by chance. From a mathematical point of view, the double ring orientation is almost absurd. Ring galaxies are already pretty rare. They only make up a very small percentage of all known galaxies. It is very unlikely that one ring galaxy will be right behind another. it is even more unlikely that we could see both of them in the same small field of view. Imagine you throw a coin into the air. It would be like it landing on its edge twice, but on different sides of the table at the same time. The double Hoag sight has inspired both serious scientific curiosity and playful speculation. While astronomers focus on the mechanics of alignment and the classification of the background object, the public imagination runs wild. Some see it as a sign of hidden cosmic patterns, or even as an argument for the idea that certain structures might be more common than we think if we looked deep enough. For scientists, the real value of the background twin is as a reminder. It reminds us of how much chance plays into our observations. If the background galaxy had been slightly off-center, the Hubble's famous photo would have been beautiful but less iconic. Instead, we have a frame where the improbable became a reality. It offers a visual metaphor for how the universe often hides layers within layers. There is also a small prize for noticing things. Because the twin is so far behind Hoag's object, any light we see from it has already gone by the galaxy in front. That means it has gone through the ring of gas and maybe even the dark matter around Hoag's object. In theory, studying that light could give scientists secondary knowledge about the properties of the material around Hoag's object. It would be like using nature as a backlight for a study we could never plan. So far, no in-depth follow-up has shown us much more about the smaller Hoag. This is mostly because it is so faint that long scans are needed, and telescope time is always in high demand. Still, it is one of the strange things about Hoag's object that makes it stand out. It is a very rare and orderly galaxy in its own right, and its most famous picture is shared with what might be a cousin from a very far away. A cousin seen billions of light years away. The age paradox of the ring's stars. The ages of Hoag's object's stars are one of the most interesting clues to its past, but they also add to the puzzle instead of solving it. The golden core is made up of stars that are billions of years old. They glow with the warm yellow light that comes from fully grown stars. That part makes sense. Cores that look like an ellipse are usually made up of older populations, but the ring is a whole different thing. Its bright blue color is typical of young, big stars that burn quickly and hot. Some of them are only a few million years old. This big gap in the ages is a problem. Galaxies usually have smoother changes in the number of stars in their populations. Usually stars get younger toward the edges as you move from the older ones in the middle. But in Hoag's object, there is a sharp break between the old stars in the core and the young stars in the ring. The empty space in the middle acts as a dividing line. It looks like two different galaxy timelines were squished together into one picture. Spectroscopic studies reinforce the visual impression. By breaking the light from the ring into its component wavelengths, astronomers can identify chemical fingerprints. They can identify fingerprints of different types of stars and estimate their ages. These studies show that many of the stars in the ring are extremely young, less than 10 million years old. Meanwhile, others are a few 100 million years old. This suggests that the ring has been forming stars for a long time, but is still actively producing them today. The core, by contrast, has not formed new stars in billions of years. This raises an obvious question. If the core is old and dormant, where is the fuel for the ring's ongoing star formation coming from young stars require dense cold gas clouds to form? That gas must have been collected into the ring somehow. But without nearby galaxies to donate material and without signs of a recent collision, the source remains a puzzle. Some astronomers propose that the gas might have been slowly accreted from the intergalactic medium. This is the thin soup of gas that exists between galaxies. In this scenario, Hoag's object could have pulled in streams of pristine hydrogen over hundreds of millions of years. This hydrogen would then settle into stable orbits in the ring and begin to form stars. But while this could explain the continued youth of the ring, it doesn't explain its precision. It doesn't explain its perfect circular shape. An inflowing gas is usually messy, leading to warped disks or irregular structures. Some people think that the age difference might be because of a past interaction that brought in new gas. This interaction would have mostly left the core alone. For instance, a dwarf galaxy full of gas could have been shaken up. This would cause its matter to settle into a ring and help stars to form. This would explain why the stars in the ring are so young, but it is hard to be sure without seeing any leftover rocks or tidal tails. The age paradox also forces us to think about the time scales. If the ring was formed quickly in a single event, the stars in it should be roughly the same age. They would have only slight variations, but the data suggest a range of ages. This means that star formation in the ring has been sustained over a significant period of time. Whatever created the ring didn't just trigger a one-time burst. It set up the conditions for a star formation that have lasted for hundreds of millions of years. The chemical makeup of the stars in the ring doesn't exactly match that of the core. This is a small but important feature. It looks like the ring's stars were formed from a gas that had a different evolutionary past. They have a little less of the stronger elements. This makes it more likely that the ring's material came from somewhere else besides the core's leftovers. The paradox of age tells us that Hoag's object has two separate histories locked together in one galaxy. It has an old inactive heart and a young active halo. They are not changing at the same rate, and there does not seem to be a clear way to connect them either physically or in terms of time. It is like finding a castle from the Middle Ages exactly surrounded by the skyline of a modern city. A city with no sign of the ages that came before or after. No spiral arms, no bar, no disorder. Although galaxies come in many forms, they tend to stick to a few well-known trends. There are spirals with beautiful arms that wind around a bright center. There are barred spirals with a bar of stars in the middle that feeds matter into the arms. And there are ellipticals, which are mostly made up of old stars and are smooth and simple. It doesn't matter how jumbled irregular galaxies look, they still have their own way of being structured. But Hoag's object is different. It doesn't fit neatly into any group. It is most different from other things because it doesn't have any twisting arms. In the local universe, spiral galaxies are the most common type. A lot of star formation takes place in their arms. Density waves shape these arms. These are areas of higher gravity that move through the disk and squeeze gas together to make new star groups. The shapes in Hoag's object, on the other hand, are not twisting. The thing's ring is not an arm that is bent into a loop. It is a different circle that doesn't seem to be connected to the core by a spiral pattern. It also lacks a central bar. In barred spirals, a straight line of stars stretches through the core. It acts like a conveyor belt that funnels gas toward the center and helps shape the galaxy's evolution. Without a bar, the usual spiral bar dynamic is absent. In fact, Hoag's object's core is more like an elliptical galaxy, smooth, round, and devoid of dust lanes. It lacks the gas clouds or star-forming clumps typical of spirals. And then there is the surprising absence of disorder. Most galaxies, even those that look symmetrical at first glance, show asymmetries when examined closely. A spiral arm might be brighter on one side, a dust lane might cut across a part of the core, or faint tidal streams might stretch into space from past encounters. Hoag's object doesn't show these imperfections. The ring is evenly bright all the way around. The core is clean and symmetrical, and the space between them is empty. It is as though every chaotic element that usually comes with galactic evolution has been filtered out. This structural simplicity is baffling because galaxies don't usually stay clean for long. Interactions with neighbors, minor merges, and even the uneven distribution of gas and dark matter create lopsidedness. In theory, Hoag's object should show some scars from its past, but none of them are visible even under Hubble's sharp eye. Some researchers have suggested that the lack of spiral arms and a bar could be due to mass distribution. the way the galaxy's mass is distributed. If Hoag's object has a particularly stable gravitational potential, it might prevent the formation of density waves. This potential could be shaped by an unusually smooth dark matter halo, and these density waves are what give rise to arms. But this doesn't explain why the outer ring is so perfectly maintained while the interior remains empty. It is harder to explain why there is not a bar. When stars in a disk galaxy react to changes in gravity, bars tend to form on their own. They can be found in both young and old galaxies. This suggests they are a regular step in the evolution process. If Hoag's object had a bar at any point, it must have been erased. But erasing a bar generally leaves behind something like a central bulge or an inner ring. Neither of them is here. Another strange thing is that there are no dust roads. Spiral galaxies are made up of dark, winding strands of dust. These strands show how they are put together and give stars the building blocks they need. The center of Hoag's object is free of dust, and the ring doesn't have the spots that dust clouds normally make. This lack of dust may help to explain why it looks so clean, but it also means the process that made the ring did not involve violent gas-filled conditions. Conditions common for spirals. Taken together, these absences make Hoag's object something of a structural ghost, a galaxy that has shed nearly every common feature except for its core and its improbable ring. It defies the neat categories that astronomers rely on. It stands outside the usual spiral, elliptical, and regular framework. It is tempting to think of it as a finished galaxy, one that has settled into a final, stable state. But the active star formation in the ring suggests otherwise. It is still evolving, just not in a way that fits the standard blueprints. Whatever forces shaped it did so without leaving the usual fingerprints. The perfect symmetry problem. A picture of Hoag's object shows that the ring is almost exactly round. This stands out more than anything else. It is not crooked, stretched, or bent. It is the same width all the way around. And no matter what angle you look at it, it is always the same distance from the center. Really accurate things like that don't happen very often in astronomy, almost never. When you look at the size of galaxies, nature almost never makes perfectly round forms. Most ring galaxies have visible distortions. Some parts of the ring might be thicker or brighter than others. These are caused by uneven star formation or leftover debris from a collision. Even in systems with well-defined rings, gravity from nearby galaxies tends to stretch the ring. The pull of their own irregular mass distribution also tends to stretch the ring into something slightly elliptical. Hoag's object doesn't suffer from any of these flaws. The symmetry is so precise that astronomers have used it as a benchmark. They use it when testing image processing algorithms. If the software can trace a perfect circle around Hoag's object's ring, then they know it is working correctly. That is how unusually clean its outline is. The problem with such perfection is that it doesn't line up with how galaxies usually evolve. Rings are dynamic structures. Their stars move, the gas clouds drift, and external forces constantly tug at them. Even without a nearby galaxy to disturb it, internal gravitational variations should cause subtle warping. This warping of the galaxy itself should happen over millions of years. Yet Hoag's object's ring seems to be frozen in a state of geometric purity. To maintain that shape, the galaxy's mass must be distributed with an extreme precision. One possibility is that Hoag's object has an unusually smooth and spherical dark matter halo. This halo would exert a uniform gravitational pull in every direction. This could keep the ring's stars in stable circular orbits. But mapping a dark matter halo is notoriously difficult, and no study has yet confirmed this for Hoag's object. It is also possible that the ring was made in a single fast event, like a perfectly aligned impact, and it has not had much time to change shape. This idea is flawed because it doesn't fit with what we know about the universe. For example, the fact that stars have been forming in the ring for hundreds of millions of years. A short-lived event should have left behind a structure that is more uneven and temporary, not one that looks stable and busy. There are some scientists who think the uniformity could be a result of how the stars in the ring are moving. If all of their orbits are in the same plane and have very little irregularity, the ring would look like a circle. But this brings up another question. How did so many stars end up moving in such a straight line? Galaxies usually have a lot of stars moving all over the place. The empty gap between the ring and the core only adds to the puzzle. In most galaxies, even those with rings, there is some spillover of stars or gas into the space between components. Hoag's object's gap is clean, as if the ring was placed at a precise orbital distance, a distance where nothing else is allowed to linger. This sharp division enhances the visual symmetry but makes the mechanics harder to explain. Time is another issue. Things that are very stable tend to lose their balance over billions of years. Small pushes from gravity, gas flow, or star movement change the shape over time. So if Hoag's object has kept its perfect shape for a big part of its life, something is actively keeping it that way. It is still not clear if that is because of dark matter, the balance of orbital resonances, or some other unknown force. This desire for perfection is what keeps Hoag's object at the center of the discussion. When scientists try to use known physics to explain it, they have to choose. They must choose between keeping the symmetry and explaining how stars are being formed. It seems like the galaxy is where two impossible events meet, and both of them have to be true at the same time. The missing dark matter clues. Dark matter has been one of the most effective tools in science for many years. We cannot see it, but we can feel how it affects us. Most galaxies have dark matter that can be seen in the way that stars and gas move. This is especially true in the outer parts of the galaxy. Here, visible matter alone cannot explain the speeds that can be seen. Astronomers can get a rough idea of how much dark matter a galaxy has. They do this by comparing its visible light to the movements of its stars. But with Hoag's object, the results have not been so straightforward. Its rotation measurements don't perfectly match the patterns we would expect. The speeds at which the stars in the ring and core move don't match a standard dark matter halo. In many galaxies, rotation curves stay flat or even rise slightly at large distances from the center. This is a sign that dark matter's gravitational pull dominates in the outskirts. Hoag's object's data suggests something different. The ring stars are not moving as fast as expected for a galaxy of its size. It's as though the dark matter halo is weaker or is shaped in an unusual way. One theory is that Hoag's object's dark matter halo is not as dense as usual. This means it has less of this unseen stuff compared to its gas and its stars. It is thought that ring galaxies need strong dark matter halos to keep their shape, so that would be very strange. If there was not enough dark matter, gravity instability would make the ring bend or break apart over time. But Hoag's object's ring is solid and even. It is also plausible that the dark matter is spread out in a different way than normal. In a lot of galaxies, the halo is circular and has a smooth density that rises toward the center. But Hoag's object could have a halo that is flatter or is less even, or it could have an edge that is particularly sharp. This would change the paths of its stars in strange ways. This might also help to explain why the space between the core and the ring is so clean. If the gravity field there is not stable for star motions, then matter would not be able to stay there. Some astronomers have even speculated that Hoag's object could be an example of a galaxy with modified gravity. This is an alternative to dark matter. These theories suggest that our understanding of gravity itself changes at very low accelerations. This would remove the need for dark matter in certain cases. While it is controversial, Hoag's object's odd rotation profile is exactly the sort of anomaly that makes scientists test these ideas. What complicates the problem is that dark matter is also involved in how galaxies acquire and retain gas. The dark matter halo's pull on gas keeps it from leaving in most galaxies. This keeps star creation going. How has Hoag's object managed to gather and maintain the gas that drives the ring's star creation? How has it done this if its halo is weaker or has a different shape? If the dome was not there, the ring might have broken apart a long time ago. The galaxy's seclusion adds another element to this enigma. Hoag's object should be a pretty clean place to study the spread of dark matter. This is because it is not near any galaxies that could affect it. There is an idea that this makes it easier to measure. We do not have to take into account the pull of our neighbor's gravity. Now, even with that benefit, the data still doesn't fit into the usual halo model. Hoag's object is situated at a distance of approximately 600 million light-years. This contributes to the challenge. It is harder to get very accurate speed readings at that distance. This is especially true for the faint stars in the outer ring. Astronomers use the movement of gas clouds as markers, but these readings can be thrown off by things like the winds that make stars or small changes in the past. We might have a better idea of the galaxy's true dark matter profile when we get new telescopes. But for now, the numbers do not give us much confidence. The Hubble's 2002 high-resolution study. When the Hubble Space Telescope looked at Hoag's object in 2002, it had already been interesting to scientists. It had been interesting for more than 50 years, but the earlier pictures taken from the ground were missing the fine details. They were amazing for the time, but details were needed to figure out what they were hiding. That changed right away with Hubble's high-resolution view. It made an image of the galaxy that was so clear and so even. It became one of the most famous pictures of the early 2000s. It also sparked a new wave of interest in science and the public. Before Hubble-Hoag's object appeared as a blurry core surrounded by a faint ring, its edges were softened by the limitations of the Earth's atmosphere. The basic structure was visible, but the finer points were hidden in the blur. The even spacing of the stars in the ring, the emptiness of the gap, the pristine nature of the core. With Hubble's advanced optics and its position above the atmosphere, those details came into sharp focus for the first time. The 2002 images revealed that the ring was not just a vague band of light. It was composed of thousands of hot young blue stars packed into a narrow zone. Their combined glow was outlining the ring like a neon halo in deep space. The width of the ring was surprisingly consistent all the way around, and the distribution of the star clusters was remarkably even. There was no clumping and no visible disruptions. The core, too, came into sharper definition. Instead of a messy central bulge, it appeared to be smooth and golden. Its older stars were blending into a flawless sphere. There were no dust lanes slicing across it, no obvious star-forming regions, and no irregularities to hint at recent turbulence. This smoothness was part of what made the Hubble image so captivating. It was a galaxy that looked almost manufactured in its perfection. The background twin was one of the most surprising things that Hubble's picture showed us. This is the smaller, farther away, ring-shaped galaxy, perfectly lined up in the space between the core and the outer ring. It was very small and faint, but it duplicated Hoag's object's structure in miniature. This made it look like a double ring galaxy. People talked about how statistically unlikely it is for things to line up in this way. This made the picture go viral. Aside from being beautiful, the pictures gave the experts useful information. Astronomers could improve their predictions of stellar ages by examining the colors of the stars. They examined the stars in both the core and the ring. The yellow tones in the core showed that it was made up of older, cooler stars, while the bright blue light in the ring showed that it was made up of huge, short-lived stars, stars that were only a few million years old. The big difference in age and color made it even more mysterious. Mysterious how the two buildings came to be and changed over time. The level of symmetry seen in the Hubble images also made it possible to test theories about its formation. For example, if the ring had formed from a collision, astronomers would expect to see signs of distortion, things like uneven star formation or faint tidal debris, none of which were present in the high-resolution data. This absence of expected features pushed some researchers toward alternative explanations. Explanations like resonance patterns or unusually stable gravitational environments. Hubble's study did not solve the riddle of Hoag's object, but it made the puzzle sharper. The clean lines and flawless geometry seen in the images forced scientists to confront just how rare such a structure is. Many proposed scenarios failed simply because they could not produce something so perfect. They couldn't do it without leaving behind telltale scars. The pictures also changed a culture. A lot of people saw them in astronomy outreach programs, textbooks, and internet groups. They were often used to show how beautiful and strange the world is. Some people who had never paid much attention to galaxies before were amazed by its symmetry. For some of them, Hoag's object was the first time they had heard of the idea that objects in space can be both natural and amazingly beautiful. The gas halo mystery. The mystery of Hoag's object lies in the invisible halo of gas that is circling the galaxy. It is not in the bright blue ring or the golden heart. Scientists have found a large area of hydrogen gas that goes far beyond the outer ring. It is faint, but radio telescopes that are precise enough can measure it. That might not seem strange by itself. A lot of galaxies have gas halos. We expect Hoag's object's ring to act in a certain way, but it doesn't. In most galaxies, especially those actively forming stars, the gas halo is dynamic. Streams of gas flow inward, fueling star birth, while other streams are pushed outward by stellar winds, supernova explosions, or a central black hole. These inflows and outflows give the halo a patchy, turbulent structure. It gets hotspots where gas is being compressed and voids where it has been blown away. Hoag's object's halo, by contrast, looks remarkably smooth and undisturbed. The gas halo doesn't show the obvious signs of motion toward or away from the galaxy. Spectroscopic studies measuring the Doppler shift of a hydrogen emission line find very little net movement. This happens in either direction. That means that the gas is not clearly feeding the ring's star formation, nor is it being ejected in powerful flows. It just seems to sit there extended in a calm bubble around the galaxy. It is like a mist that is frozen in place. This is a problem for our models of how galaxies sustain star formation. The outer ring of Hoag's object is still actively producing young, massive stars. These require a steady supply of dense, cold gas. If the halo is not delivering that gas to the ring, then where is the fuel coming from? Some astronomers speculate that small amounts of gas may be trickling in gradually, too subtly to detect directly. But even that would require an unusually stable transfer process to avoid disturbing the halo's shape. The size of the gas cloud is another unknown. Estimates show that it goes far beyond the visible ring. It sometimes reaches 2 to 3 times the diameter of the main structure of the galaxy. That is a huge amount of space for a galaxy that looks like it is all by itself. It is not clear how Hoag's object got such a huge gas store in the first place, especially if it did not have nearby galaxies that could add extra gas through tidal interactions. The smoothness of the halo also hints at an absence of violent events in the recent past. In many galaxies, mergers or close encounters leave clear marks in the gas distribution, marks like streams, shells, or irregular clumps. Hoag's object's halo has none of these. This suggests that it has not been significantly disturbed for hundreds of millions of years. This level of stability might help to preserve the ring's perfect symmetry, but it also makes the galaxy harder to explain in terms of typical ring formation scenarios. These usually involve some kind of disruptive event. Some researchers have floated the idea that the halo could be a remnant, a remnant from an earlier stage in the galaxy's life, perhaps left over from when the ring itself was formed. If the ring was created by a massive inflow of gas, the leftover material could have spread outward. This could have been from a merger, a captured gas cloud, or a resonance effect. It would have formed the current halo. Over time, the more chaotic parts would have settled, leaving behind the calm structure we see today. But if that is the case, it raises another question. Why has not more of that gas fallen inward to fuel even more star formation? The halo's strange behavior might also have something to do with Hoag's object's dark matter spread. If the dark matter ring is a strangely smooth spherical shape, it might help keep the gas envelope stable. It would do this by spreading out the gravity forces evenly. The gas might not be falling in too fast because of this too. It might be held in a state of balance by a gravity that is pulling it in and a pressure that is pushing it out. The metallicity puzzle. In astronomy, metallicity is a measure of how many elements heavier than hydrogen and helium a star or gas cloud contains. These heavier elements are called metals in astrophysics. They are forged inside stars and spread into space when those stars die. Over cosmic time, successive generations of stars enrich a galaxy's gas with more and more metals. That is why older stars generally have lower metallicity, while younger stars tend to form from metal-rich gas. Hoag's object, however, does not quite follow this rule. Studies of its ring's metallicity have revealed something strange. The young blue stars in the outer ring have a chemical composition that doesn't match what we would expect. We would not expect it if they had formed from the core's enriched material. Instead, their metallicity is significantly lower than that of the core's stars. This resembles the chemical signature of a gas that has had a very different evolutionary history. This is important because it shows that the ring was not just made by pushing the inside gas outward. What if that were true? The gas in the ring would also be high in metals because it would have come from the same place. The low metallicity instead points to a source that is outside the galaxy, a new gas that came from there. It is possible that Hoag's object caught a huge cloud of almost pure hydrogen from the space between galaxies. This would explain both the lower metallicity and the fact that stars are still being formed in the ring. It is hard to explain, though, how such a large amount of gas could be captured without any clear signs of disorder. Disorder like tidal tails, imbalances, or debris. Another concept is that the ring might be what is left of a gas-filled dwarf galaxy that Hoag's object ate up. In this case, the dwarf's gas settled into a circle around the core and started to make stars. This could fit the chemistry scene because small galaxies tend to have less metal than bigger ones. But once more, this idea is not supported by enough data. The stars from such a dwarf are not visible, and the ring's perfect symmetry doesn't fit with how merger remnants usually look. The metallicity puzzle gets even more interesting when you look at the distribution of metals within the ring itself. Observations show that the metallicity is relatively uniform all the way around. It is not patchy or showing gradients. In most galaxies, metallicity tends to vary depending on location. This reflects the complex history of gas flows, star formation, and supernova feedback. Hoag's object's ring appears to be almost too even. This suggests that whatever process brought the gas there mixed it thoroughly before star formation began. This level of chemical uniformity is hard to achieve without turbulence or rotational mixing, and yet the ring doesn't show signs of being stirred up by violent processes. That implies a gentle, controlled settling of gas into the ring. This again clashes with the high-energy events usually invoked to explain ring formation. There is another problem with the metallicity data. The stars in the ring do not have as much metal as the stars in the core, but they are not very basic either. They still have stronger elements in them like oxygen, nitrogen, and iron. This means that the gas they were formed from had already been through at least one generation of star formation. That rules out the thought that the gas is truly primordial. meaning it has not changed since the Big Bang. However, it does leave open the question of where it came from and how it got to be arranged in such a strange way. There is a difference in the amount of metals in the core and the ring. Some scientists think this could help us to figure out how old the galaxy is. If the core was formed early in the universe's past and got rid of most of its gas, it might have stayed chemically stable. Later, a new flow of less enriched gas could have formed the ring. This would give the galaxy two different histories of its history. Along with the other proof that the core and the ring are not only different in shape, this idea makes sense. The core's rotation secret. Scientists who study galaxies often find that the center parts move at the same speed as the structures around them. When it comes to spiral galaxies, the bulge and the arms rotate in a way that is similar to each other. But when it comes to elliptical galaxies, the whole system tends to move as one, though it is less organized. In a small but important way, Hoag's object breaks this rule. The shining ring around its golden center spins much more slowly than the core itself. This was found by measuring the changes in the Doppler shifts of light from the stars in both areas. It looks like the stars in the ring are moving around the galaxy at the same speed as an actively spinning disk. The spinning curve flattens out to a crawl in the core though. It is as if the galaxy's heart is moving more slowly than its outer shell. This difference is not just a strange thing. It is a clear sign that the core and the ring may not have come from the same place. If the ring had formed naturally as an extension of the core's own disk, we would expect their rotation speeds to be linked. The core would be providing the gravitational anchor for the ring's motion. Instead, the ring's faster rotation suggests it might be orbiting around not just the core, it might also be orbiting the galaxy's broader dark matter halo, while the core itself plays a smaller role. The heart might be the remains of an older elliptical galaxy, which rotates more slowly than disk galaxies. If Hoag's object was formed as an oval shape at first, and the ring was added later, the difference in spin would make sense. Perhaps it was by capturing an outside gas storage. The old core would continue to rotate slowly, while the new ring would move at a speed set by the bigger gravity structure. The smooth change from the slow-spinning core to the fast-spinning ring is another interesting feature. In many galaxies with parts that do not fit together right, there is a zone in the middle where the two movements mix. This makes structures twist or star paths go off in strange directions. There is none of that in Hoag's object. There is a clear separation between the two regimes. This is because the space between the core and the ring is mostly empty. They may be rotating in very different ways because they are not physically connected. They are not touching strongly enough to sync up over time. Researchers have pointed out that the slow core rotation could also be linked to its pristine dust-free appearance. In galaxies, gas inflows often spin up the core over billions of years. This happens by adding mass and by exerting a gravitational torque. Without a steady supply of gas, the core's rotation can stagnate. Hoag's object's gas supply appears to be concentrated entirely in the ring and the surrounding halo. This leaves the core to evolve passively and slowly. The slow spin also has implications for the galaxy's central black hole if one exists. In many galaxies, the rotation of the core helps to feed material into the black hole. This fuels bursts of energy that can be seen across the electromagnetic spectrum. In Hoag's object, the lack of such activity could be a result of the core's sluggish motion. It is unusually quiet in radio and X-ray wavelengths. This motion doesn't deliver gas efficiently to the center. There is a lingering question about whether the core's rotation rate has always been this low. If the ring was formed relatively recently on a cosmic timescale, say within the last billion years, there might not have been enough time. Not enough time for gravitational interactions to speed up the core. Over the next few billion years, as the ring and the core subtly tug on each other, their motions could begin to align. If so, we may be looking at Hoag's object in a rare transitional phase. Caught between two different dynamic states, the galaxy's odd isolation may have kept the slow spin going for a long time. Since there are not any close galaxies to push on the core, there is nothing to move its rotational momentum. This might make it possible for it to stay in this almost separated state forever, like a fossil from its earlier days with a much more active shell around it, the ring starburst without a trigger. There is a clear reason why starbursts happen in most galaxies. They are strong bursts of star formation. If a smaller galaxy crashes into a bigger one, the gas could be squished together into thick clouds. This would spark the birth of new stars. Or the tidal forces from a close pass with a neighboring star could push gas inward. This would cause many stars to form quickly. However, in Hoag's object, the bright blue ring is busy making new big stars. It's doing this without any of the normal signs of a trigger event. Spectroscopic studies reveal that the ring is rich in hot, short-lived O and B-type stars. These are the kind that burn bright and die young, often within a few million years. Their presence means that star formation in the ring is not just ongoing, it is vigorous. Yet when astronomers look for the typical clues of what might have set off this activity, they come up empty. There is no evidence of a recent galactic collision, no streams of stellar debris, and no distorted shapes. There are no asymmetrical clumps in the ring's structure. The galaxy is in a remarkably isolated patch of space. This makes a close encounter with another large galaxy extremely unlikely. In the recent past, even the smaller background twin galaxy seen in Hubble's famous image is far behind. It's far behind Hoag's object, with no gravitational connection. So where is the fuel for this starburst coming from, and why is it arranged so perfectly in a ring? One idea is that the gas-fueling star formation has been part of the ring for a long time, perhaps for billions of years, and it is only now condensing into stars. But if that were true, the ring should show signs of gas depletion over time, with the bursts tapering off. Instead, the activity is spread evenly, which suggests a steady replenishment of star-forming material. There is also a chance that the ring is a kind of self-sustaining structure. As new stars and supernovae form, they can send shock waves through the space around them. These waves can sometimes cause more stars to form in nearby areas. If the ring's structure naturally sends these shock waves around its edge, it could set off a feedback loop. This loop would keep the process going without the need for an outside signal. Still, this does not answer the question of how the ring was set up to allow such a stable loop in the first place. The metallicity of the ring's stars, as we discussed earlier, also plays a role here. Their relatively low heavy element content suggests the gas is either from an external, less enriched source, or it has been relatively untouched by multiple generations of star birth. A low metallicity gas cools less efficiently. This means that it resists collapsing into stars unless something gives it a push. That makes the ring's ongoing activity even more surprising. It is as if the galaxy found a way to coax a stubborn gas into forming stars at a steady rate. The galaxy's dark matter ring is another thing to think about. If the halo is unusually round and smooth, it might make a stable gravitational environment for the ring. This would let the gas clouds circle without getting messed up. Over time, the ring's small instabilities or density waves could sometimes squeeze the gas just enough to make new stars. There would be no violence or short-lived events like a crash in this process. It would be gentle and last a long time. There is also the interesting but untested idea that the ring's starburst could be caused by an interaction we cannot see. For example, a very small companion galaxy could be moving through the ring, one that is too faint for our current sensors to pick up. This could be sending out waves of compression. If such an object existed, it would be very dim and almost perfectly lined up. Lined up so as not to mess up the balance of the ring. A possible resonance ring formation, the beautiful ring on Hoag's object, might have been formed through a process called orbital resonance. This is one of the more captivating ideas about how it appeared. When different parts of a galaxy interact in a way that makes their motions match up, this is called a resonance. These parts could be the paths of stars and gas clouds, or even nearby celestial things. This synchronization can focus matter in certain areas, making patterns like rings or gaps. This is something we can see in the rings of Saturn. These are caused by resonances with its moons. Applied to galaxies, resonance rings usually form when a rotating bar or spiral pattern inside the galaxy exerts a pull, a periodic gravitational tug on the surrounding stars and gas. Over time, material gets trapped at certain orbital distances. This is where the pattern's rotation and the star's orbital periods line up. The trapped material piles up, forming a ring. In Hoag's object, however, the situation is more puzzling. For a resonance to work in the traditional sense, the galaxy needs an internal structure like a bar or spiral arms. This structure would drive the process. Hoag's object has neither of these. Its core is a smooth, dust-free sphere, and there is no sign of an internal bar that could be shepherding gas into a ring. Without that driver, the standard resonance ring model doesn't fit neatly. A number of researchers think that the resonance might not have been caused by something inside the star. Instead, it could have been caused by something outside the star. For example, a small galaxy may have passed close by a long time ago. Its gravity could have pulled on Hoag's object just enough to set up the circular pattern. The perturber would have to be long gone by now if that is the case. It would leave only the ring as proof of its presence. This ghost resonance idea is interesting because it doesn't need a continuous bar or spiral pattern, but it is hard to show without finding the person who did it. It is also possible that the vibration is caused by the dark matter ring around the galaxy. If the halo has a strange density profile or a small imbalance, it might change the paths of stars and gas. This might make rings more likely to form. There is a lot of theory in this area because dark matter is invisible but has real gravitational effects. And in cases like Hoag's object where normal theories do not work, it is tempting to look for answers in unseen things. A big challenge for the resonance theory is that it typically produces rings with some irregularities. In most observed resonance rings, you can spot brighter clumps where star formation is more active, or you might see slight differences in thickness around the circumference. Hoag's object's ring, by contrast, is eerily smooth and consistent. If a resonance is at work, it is producing a level of symmetry that is virtually unheard of in other galaxies. Computer simulations have tried to reproduce this effect, but so far they struggle. When you set up a galaxy with a smooth core and try to generate a ring purely through gravitational resonance, the result is usually lopsided, or it is a slightly warped structure. To get something as perfect as Hoag's object, simulations often need to start with very specific, finely tuned initial conditions, the kind that make astronomers wonder if we are looking at an extremely rare one-off event rather than a repeatable process. The resonance theory remains on the table because it does account for one important detail: the stability of the ring over time. If stars and gas are locked into resonant orbits, they can maintain their positions for billions of years. They would avoid the collisions and dispersal that would otherwise blur the ring's shape. This could explain how Hoag's object has stayed so pristine for so long, even in the absence of recent external influences. What is missing is direct proof, like a measurable pattern in the way the stars in the ring move. A pattern that fits with what a resonance model says should happen. In the future, instruments with higher precision than Hubble might be able to find this kind of pattern. But for now, the resonance theory is just an idea that has not been proven with a smoking gun. If a resonance really is the answer, then Hoag's object would be one of the most extreme examples of this effect, perhaps even the only example. That would make the puzzle even bigger, since we would have to give up yet another good idea for how this perfect galaxy ring was formed. The lens galaxy theory, which was rejected. People who study astronomy first heard about Hoag's object around the middle of the 20th century. One of the first theories was that it might not even be a strange galaxy. Instead, it could be an illusion caused by a gravitational lensing. When a big object like a galaxy or a cluster bends light from behind it, this is called gravitational lensing. It can make arcs, rings, or multiple images. An Einstein ring is a nearly perfect circle of light. It can sometimes be made when everything is lined up perfectly. Hoag's object looks like it could be one of these cosmic optical tricks. A bright, central lens surrounded by a flawless ring of light is exactly what you might expect from an Einstein ring. The idea seemed tempting. Maybe the golden core is a closer galaxy, and the ring is actually a distorted view of a more distant galaxy's light bent around it. This would have been a neat, well-understood explanation. It would require no exotic physics or a 1 in a billion galactic formation scenario. As soon as astronomers studied Hoag's object in more detail, the lensing theory began to unravel. The first blow came from spectroscopy. When scientists measured the light from the core and the ring separately, they found they had the same redshift. This means that they are at the same distance from the Earth. If the ring were from a background galaxy, its redshift would be significantly higher. This would reflect its greater distance. Instead, the data showed that the ring and the core are physically part of the same structure. The inside features of the ring were another nail in the coffin. Gravitational lensing can stretch and make faraway things bigger, but it can also warp them. You could see lines of light, repeating designs, or smeared details. Its ring, on the other hand, has star groups that are clearly defined and evenly spread. They are not distorted. This is what you would see if you looked at the ring directly instead of through the distorted lens of gravity. For gravity lensing to make such a perfect, thick and uniform ring, the lensing mass would have to be very large, much bigger than Hoag's object's small circular core. Usually clean Einstein rings can only be made by galaxy groups or giant galaxies with very large dark matter halos. The heart of Hoag's object doesn't have enough mass to bend light in this way on this small of a scale. Another point against the lensing idea is the empty gap between the core and the ring. In an Einstein ring, the light is bent around the lens, but there is no requirement for a clean void in between. Often you would see additional light from the lensed object spilling toward the center. In Hoag's object, the gap is truly empty of stars. This matches the idea of a physically starless zone, not an optical illusion. The theory also had trouble explaining the galaxy's motion. Observations of the ring's rotation show that it is moving in a way consistent with being bound to the core's gravity. In a lensing scenario, there would be no such connection. The background galaxy's light would not move in sync with the foreground object. The matching dynamics were one of the final pieces of evidence that proved the core and the ring are part of the same galaxy. The lensing idea was mostly dead by the time Hubble took a picture of Hoag's object in 2002. The clear picture showed not only the evenly spread star clusters in the ring, it also showed the faint structure of the twin galaxy far behind Hoag's object. This showed that the image looks very different from the galaxy's main structure when a gravitational lensing is present, a radio silence, a lack of strong emissions. Astronomers do not just look at galaxies in visible light, they also listen for radio waves. Radio waves can show things that are not visible. Things like how stars are formed deep in dust clouds, how black holes shoot out jets of energy, or how faint hydrogen gas spreads. Radio waves make many ring galaxies shine brightly, especially those making stars very quickly. This is because of the powerful events going on inside them. Hoag's object, on the other hand, is surprisingly quiet. Radio surveys have detected only faint emissions from Hoag's object, and those signals are far weaker than expected for a galaxy with an active star-forming ring. Normally, massive young stars in such a ring would end their lives as supernovae. This would accelerate cosmic rays and produce strong synchrotron radiation, a hallmark of vigorous starbirth. Yet in Hoag's object, the radio brightness is barely above the detection threshold. This lack of a strong radio output is puzzling for several reasons. First, it suggests that either the rate of massive star formation is lower than the optical images imply, or the supernovae are somehow less efficient at producing cosmic rays. The bright blue color of the ring indicates plenty of hot, short-lived stars, so the first explanation doesn't seem to fit. That leaves the possibility that the galaxy's environment is somehow suppressing the usual chain of events, the chain of events that leads to radio emission. At least one idea says that Hoag's object has a weaker interstellar magnetic field than most galaxies. A lot of the synchrotron radiation seen at radio wavelengths comes from cosmic rays spiraling along magnetic field lines. Even if supernovae are happening at the normal rate, the radio emission would go down if the field is especially weak. This is because fewer cosmic rays would be caught. The magnetic fields in galaxies are extremely hard to measure, but Hoag's object could become a great example of how these fields affect a galaxy's radio voice. It is also likely that the gas in the ring is spread out in an odd way. In many starburst areas, thick pockets of gas and dust keep energetic particles from supernovae in check. This raises the radio output in the area. If Hoag's object's gas is spread out more evenly, these particles might be able to escape into space. They could escape between the galaxies before they give off a big signal. This fits with the other strange things about the galaxy, like the straight line of gas in the halo and the lack of swirling. The quietness in radio wavelengths also extends to the galaxy's core. Many galaxies, even relatively inactive ones, emit at least a small amount of radio energy from their central black holes. In some cases, these emissions come from low-powered jets or from a hot gas swirling near the event horizon. Hoag's object shows no sign of such activity. This is further reinforcing the idea that its core is unusually passive. This fits with other clues like the slow core rotation and the absence of dust lanes or gas inflows. The hydrogen line emissions that astronomers often use to trace cold gas in galaxies are faint here as well. This does not mean that the galaxy lacks gas. We know from other observations that it has a large halo, but it suggests that much of the gas is either too diffuse or too smoothly distributed to produce strong localized signals. Again, this matches the theme of Hoag's object as a system where everything seems stable to the point of being almost static. From a bigger picture point of view, the radio silence could be telling us something. Hoag's object is not only an optical oddity, but also an abnormality of more than one wavelength. Most galaxies that look as strange as this one sound strange when viewed through radio waves. This is usually because the same forces that shape them also send out strong radio waves, forces like collisions, mergers, and strong gravity interactions. It seems that whatever formed Hoag's object was a rare, peaceful event, or at least one that happened a long time ago so that all of its energy effects have worn off. Future radio devices like the Square Kilometre Array might be able to make more detailed maps of Hoag's object signals. This could help us to find faint structures we have not seen before. They should still only show a faint whisper of radio energy on those maps. That would prove that this galaxy is truly unique, a beautiful part of the universe that values quiet over a show. The ultra-smooth core, the golden heart of Hoag's object, is not only unique because of its color and slow spinning, it is also unique because it looks so clean. You can find small irregularities in the cores of most galaxies, even in elliptical galaxies that are generally calm. These can be weak dust lanes, wisps of gas, or small star groups spread out on the surface. These are the marks of internal activity merges and gas flows that have happened over billions of years. But in Hoag's object, the core is so clean that it is almost scary. When the Hubble Space Telescope imaged the galaxy in 2002, its resolution was sharp enough to reveal tiny details across the central sphere. Astronomers expected to find at least some mottling. Mottling is variations in brightness that indicate dust clouds or younger stellar populations. Instead, the core's surface brightness is nearly uniform, like a smooth ball of ancient stars. There are no visible dust filaments cutting across it, no pockets of blue stars, and no telltale knots of recent star formation. This kind of cleanliness is rare because galactic cores tend to be messy places. Gas from the outer regions usually drifts inward over time, feeding bursts of new star formation. Or it fuels a central black hole. In the process, dust accumulates, shaping lanes or swirls that break up the light. Even in galaxies without active merges, minor interactions with passing satellites can disturb the central regions. The fact that Hoag's object's core shows none of these signs suggests an extraordinary level of long-term isolation. The smoothness also supports the idea that the core may be a very old stellar population. Spectroscopic studies indicate that most of its stars are yellowish. This is similar to the older stars found in elliptical galaxies. If the core has not had a significant influx of fresh gas in billions of years, then no new stars would form. This would leave only these ancient, evenly distributed stars to dominate its appearance. The mystery is not just that the core is old. It is that it has stayed untouched for so long despite the active star-forming ring around it. In a typical galaxy, material from a star-forming outer disk can drift inward due to gravity. It would eventually settle into the core, but the vast empty gap between Hoag's object's core and its ring seems to act like a barrier. It seems to prevent gas from migrating inward. Without that flow, the core remains a sealed-off relic of its earliest formation phase. Some people might wonder if the smoothness is just an optical effect caused by our viewing angle. If we look down at the galaxy's axis, we might miss some structural features we could see from the side. But the ring's symmetry makes it very likely that we are looking at Hoag's object almost exactly side-on. This means that the smoothness is real and not just a trick of perspective. It is also possible that the core went through a period of intense action in the past that cleared it out totally. Strong winds from a supernova or a time when black holes were more active could have blown away any gas and dust, any gas that was still there. This would leave only the stars. With so many years between then and now, the core would have had plenty of time to become as calm and even as it is now. The catch is that we do not see any lasting signs of such an event. There are no shells of ejected gas, no shock fronts, and nothing else that would show the violence that might have made such perfection possible. This very smoothness is not just a matter of taste. It helps us to figure out how the galaxy came to be. A core that is this clean either means the formation process was very gentle from the start, or that any rough spots were smoothed out with surgical precision a very long time ago. In both cases, it does not fit well into our usual models of how galaxies form and evolve. These models say that there will almost always be some amount of central irregularity, the outer ring's dynamics. The outer ring of Hoag's object looks like a perfect racetrack in space from afar. It is a bright, smooth loop of stars and gas that looks like it is frozen in place. But rings like these are not just pretty things to look at. Its stars are moving at hundreds of kilometers per second around the galaxy's center. They are keeping the balance of gravity just right. How does such a big, thin structure stay together for billions of years without falling apart or without getting smeared into a disk? Most galaxies, especially elliptical ones, have stars in the outer parts that are part of a flat disk. The pull of visible matter and an even bigger ring of dark matter keeps these stars in place. There are more problems in a ring galaxy like Hoag's object. There is a huge empty space between the ring and the core, so the ring is not held up by a constant spread of the stars inside it. Without an extra force to keep them in place, gravity would finally push the stars closer or farther apart. This would change the shape of the ring over time. One of the stabilizing factors is the galaxy's dark matter halo. Observations suggest that Hoag's object is embedded in a massive, roughly spherical halo of dark matter. This halo extends well beyond the visible ring. This halo provides an invisible gravitational framework that is holding the ring's stars in place, holding them along stable, nearly circular orbits. Without this hidden mass, the ring would likely dissolve within a few 100 million years. The smoothness of the ring's rotation is another clue. When astronomers measure the Doppler shifts of the stars and gas around the ring's circumference, they find something. They find that the orbital speeds are remarkably uniform. In other ring galaxies, small irregularities in speed can cause clumps, warps, or breaks over time. Hoag's object seems to avoid this fate. This is possibly because the mass distribution in its halo and its core is unusually even. A symmetrical gravitational field would keep the orbits aligned. This would allow the ring to remain both stable and perfectly circular. The gas dynamics also play a role. The ring contains not only stars but also significant amounts of gas which behaves differently from stars. Gas clouds can collide, merge, and dissipate energy, gradually settling into a common orbital plane. This process can smooth out irregularities and help the ring to maintain its shape. It can help even if the individual stars have slightly different orbital paths. The catch is that this also tends to cause gas to drift inward. This is something that clearly is not happening here in large amounts, or the core would not be so empty. According to some astronomers, the ring may be self-regulating due to star formation feedback. When new stars and supernovae form, they can send shock waves through the space around them. These waves can sometimes cause more stars to form in nearby areas. If the ring's structure naturally sends these shock waves around its edge, it could set off a feedback loop. This loop would keep the process going without the need for an outside signal. It is possible that the stars that make the ring keep it stable over time. If that is the case, then the width of the ring is much smaller than its diameter, which is another interesting fact. The fact that it is so narrow means that the paths of its stars and gas clouds are very closely lined up. In many galaxies, the close object's gravitational pull can tilt or stretch these orbits. This makes the ring thicker over time. The fact that Hoag's object is so far away in space may be its best defense. It can grow without being affected by the gravitational nudges that would usually mess up its accuracy. Even so, simulations of galactic dynamics often fail to produce a ring like Hoag's object, a ring that can last for billions of years. In most models, either the ring collapses inward to form a disk, or it disperses into a more irregular arrangement. This suggests that Hoag's object might have started with an unusually favorable set of initial conditions, perhaps a perfectly balanced distribution of dark matter gas and stars from the very beginning, and it has simply been left alone ever since. Why the simulations fail? Computer models are a big part of modern astronomy. They help us to understand how galaxies form and change over time. The known rules of physics are used in these models to make galaxies behave in different ways. Rules like gravity, the movement of gas, radiation, and the behavior of dark matter. In the last 20 years, these kinds of models have been able to explain a lot about galaxies. Things like spiral arms, explosion regions, and ring structures made when galaxies crash. It keeps on failing when it comes to Hoag's object, though. The biggest problem is reproducing the galaxy's extreme symmetry. Even with high-resolution models, the rings formed in simulations tend to be slightly oval, clumpy, or tilted. Small irregularities are normal because galaxies are chaotic systems. Their stars and gas respond to countless gravitational tugs from internal structures and nearby objects. Hoag's object, however, shows none of these expected distortions. Its ring is so perfectly circular that even the most precise models cannot match it without artificially smoothing the data. The empty space between the core and the ring is another place where things often break. More often than not, over hundreds of millions of years, gas and stars from the ring move inward. They fill the space and start new star formation closer to the core. Very much like this, galaxies like the cartwheel have gas links that connect the outer ring to the middle. Hoag's object will not follow this trend no matter what. In real life, the gap has almost no stars at all, but in computer models it goes away quickly unless certain conditions are met. The formation theories also run into trouble. In collision-based models, a smaller galaxy passing through a larger one can generate a ring structure. This happens via gravitational shock waves. This works well for galaxies with clumpy, uneven rings. But for Hoag's object, the simulations produce debris trails, asymmetrical arcs or warps that we simply do not see. In resonance-based models, where internal patterns like bars create rings, the absence of any bar in Hoag's object makes the math difficult. Even when models are adapted to remove the bar, the resulting rings in simulations tend to be unstable and fade over time. The gas composition adds another layer of complexity. Hoag's object's ring stars have a chemical makeup that doesn't match what the models predict for their formation. Simulations often assume that the gas forming the ring comes from the galaxy's original material or from a captured companion. But the metallicity profile, the amount of heavier elements in the stars in Hoag's object, doesn't match either source neatly. When these metallicity constraints are added to the models, the probability of producing a Hoag-like ring drops dramatically. Dark matter distribution is yet another sticking point. The shape and density profile of a galaxy's dark matter halo play a huge role. They determine the stability of structures like rings. In simulations, tweaking the halo to match Hoag's object's stability often results in unrealistic side effects. For instance, a halo dense enough to lock the ring in place can also cause the core to spin faster than observed, or it could lead to excessive star formation that should have left the core dustier and more irregular than it is. Even the most advanced multi-physics simulations cannot produce a galaxy that matches all of Hoag's object's known properties. These simulations combine gravitational interactions, star formation feedback, and cosmic environment effects. The models might get the ring right, but fail to match the core's smoothness. Or they might create a good-looking gap, but with an elliptical ring. There is always a trade-off, as if the galaxy is daring the laws of physics to replicate it perfectly. The failure of models does not mean our understanding of how galaxies work is wrong, but it does show us where we still do not know enough. It is possible that Hoag's object was created under a set of initial conditions that are so uncommon that they are not found in the normal model files. Or maybe there is a physical process going on here that our present understanding of physics does not fully explain. Like a strange relationship between dark matter and baryonic matter. Hoag's object is still a strange object in the world of computer-aided stargazing. Astronomers check to see if this strange galaxy finally shows up on the screen every time a new set of models is run, a comparison to the other ring galaxies. Most of the time, people talk about Hoag's object in the same breath as other ring galaxies. But when you put it next to its so-called relatives, the differences are clear. To really understand how rare it is, you need to look at cases like the Cartwheel Galaxy AM0644-741 and the Lindsay-Shapley ring. Their rings were formed in much more common ways. The Cartwheel Galaxy, which is about 500 million light-years away, is likely the second most well-known ring galaxy. At first glance, it looks like Hoag's object. It has a bright outer ring around a fainter center, but this is only a surface similarity. The ring around the cartwheel was made when two very fast-moving galaxies crashed into each other. A smaller galaxy slammed into the larger galaxy's disk. This caused shock waves that squished gas together and caused stars to form. This process left behind long, bright spokes of material, a ring with an uneven thickness, and pieces of material spread far out. Hoag's object doesn't have any of these crazy traits. The AM0644-741, sometimes called the Lindsay-Shapley ring, is another collision product. Its ring is thick, irregular, and packed with clumps where massive star-forming regions dominate. You can see clear asymmetries caused by the uneven way that the shock wave traveled through the galaxy's disk. In contrast, Hoag's object's ring is smooth, evenly bright, and so perfectly circular. So circular that no obvious collision scars can be found. This difference is crucial because even the most idealized simulations of collision rings produce some level of distortion. You can also look at the polar ring galaxies such as NGC 4650A to see how they compare. A ring of stars and gas circles at a sharp angle to the disk of the main galaxy in these systems. This is usually because material from another galaxy was taken in. They can stay stable for billions of years, but they almost always show a clear bridge of gas. Or they show a wavy transition zone where trapped matter interacts with the disk of the mother galaxy. Hoag's object doesn't have any of those things, and its ring is in the same plane as the spinning of its core. Analysts usually find trends in the metallicity of other ring galaxies. The amount of stronger elements makes sense in the context of how they were formed. In impact rings, the stars farther out usually have more metals. This is because they were formed from gas that was squeezed and made richer by recent starbursts. The metallicity of resonance rings is often the same as that of the inner disk. This is because the gas was pulled in by the structures of the galaxy. Hoag's object doesn't fit either pattern perfectly. Its metallicity profile is unique, and it doesn't match any of the common formation patterns seen in its cousins. Even the dynamics of Hoag's object's ring differ from those of other systems. In the cartwheel and AM0644-741, the ring is expanding. This is a direct result of the shock wave from the collision. Observations of Hoag's object, however, suggest that its ring is not expanding at all. Instead, it is in a long-term stable orbit around the core. This makes it more like a carefully engineered structure than the byproduct of a cosmic accident. The isolation of Hoag's object is another separating factor. Many known ring galaxies are found in environments with other nearby galaxies. This increases the chances of the kind of interactions that form ring. Hoag's object, on the other hand, sits in a relatively empty patch of space. It is far from any large neighbors that could have recently disturbed it. This solitude makes the idea of a collision or gas capture even harder to justify. A lot of scientists are having a hard time deciding what type of ring galaxy Hoag's object should be put in. It doesn't have the shape of an impact ring. It doesn't have the interior drivers of a resonance ring. And it is not lined up like a polar ring. Because of this, it is often put into the broad category of a peculiar galaxy for things that do not belong anywhere else. It is easy to see the pattern. Hoag's object is different not because it has a ring, since many galaxies do, but because it has the wrong kind of ring. Its construction, from its perfect symmetry to its chemical makeup, cannot be explained in the normal ways. The chance alignment theory. When presented with something as weird as Hoag's object, astronomers may resort to the simplest explanation. Perhaps it is not a single peculiar galaxy at all. From our point of view, it might just look like two standard galaxies lined up exactly. This chance alignment theory says that the golden center would be one galaxy, and the outer ring would be another much farther away galaxy that looks like it is wrapping around the first one. This would be just by looking at it from a certain angle. On paper, this idea has a certain appeal. It would mean that there is no need to invent an exotic formation scenario, no need to explain a massive empty gap, and no need to account for why the core and ring seem so different in color and age. But the moment that astronomers began to test it, the theory started to collapse under its own improbability. The first problem is alignment itself. For the core and ring to look so perfectly concentric, the centers of both galaxies would have to be positioned with extreme precision. They would need to be along our line of sight. Even a small offset would make the ring appear lopsided or distorted. The odds of two galaxies just happening to align in this way are staggeringly low, especially in a patch of space as sparsely populated as the one that Hoag's object occupies. The second issue comes from the redshift measurements. Redshift is the stretching of light caused by the expansion of the universe, and it directly correlates to a galaxy's distance. If the core and the ring were separate galaxies, they would almost certainly have different redshifts. This would indicate different distances from Earth. However, when astronomers examined the spectra of both the core and the ring, they found nearly identical redshift values. That means they are not just lined up in space, they are physically located at the same distance. This strongly suggests that they are part of the same gravitational system. There is also the matter of the ring's dynamics. Detailed observations reveal that the stars and gas in the ring are moving in a consistent way. They are moving as if bound to the core's gravity. If the ring were actually a background galaxy, its stars would not care about the core's mass. They would not share its rotation pattern. The fact that they do tells us that the core and the ring are interacting in a way that is only possible if they belong to the same galaxy. The empty gap is another thing that goes against the idea. We would expect to see tiny signs of the galaxy's own internal structures crossing that gap. That is, if the ring came from a background galaxy. These could be spiral arms, dust lanes, or scattered star clusters that happen to stick out across the foreground core. The gap is actually totally dark. This is what we would expect if it were really an empty space, and not just an area of overlapping projections. Some people have tried to save the chance alignment theory. They said that the light from the background galaxy is being bent into a ring by the core. But as we have already talked about, Hoag's object has a mass that is much too small to make such a perfect Einstein ring, and the visual features do not match what we see in real lensing events. Even if you ignore all the physical evidence, the statistical odds are almost insulting to the theory's credibility. Astronomers have catalogued millions of galaxies, and while chance overlaps are not uncommon, one galaxy partially blocking another perfect concentric alignments like this are virtually unheard of. To have one that also happens to share the same redshift dynamics and isolation stretches the definition of coincidence. It stretches it past a breaking point. The idea of a chance alignment had been mostly thrown out by professionals by the early 2000s. People sometimes still talk about it, usually when they are hearing about Hoag's object for the first time. This is because it seems like a cool optical trick explanation, but the more you look, the more clear it is. The ring and the core are connected and are dancing in the same gravity embrace. It was not luck that made up Hoag's object. It was a strange thing, the spectral surprises. They do not just look at the shape of a galaxy to figure out what it is made of. They also break down its light. Scientists can read Hoag's object's fingerprints by using spectroscopy to break its light into its individual bands. This lets them to figure out its chemical makeup, its temperature, its motion, and even how old its stars are. In most galaxies, the spectrum tells a pretty similar story from one part of the galaxy to another. The spectrum of the core and the spectrum of the ring do not match at all in Hoag's object, though. The core's spectrum is dominated by light from older, cooler stars. It shows strong absorption lines from elements like magnesium and calcium, the kind you would expect from an ancient stellar population that has been quietly aging for billions of years. The relative lack of emission lines, the bright spikes that signal a hot glowing gas, confirms something. There is little or no ongoing star formation in the core. This is exactly what you would expect for a golden, elliptical-like center. The ring's spectrum, however, is a completely different story. Here, the light is bluer and hotter, with strong emission lines from hydrogen and oxygen. These lines are a sign of active, ongoing star formation. Young, massive stars are flooding the surrounding gas with ultraviolet radiation. The oxygen lines also indicate that the ring's gas has been enriched by multiple generations of stars. But the enrichment level is unusual. It is higher than in some galaxies of a similar size. But it is lower than you would expect if the gas had spent billions of years recycling through the core. The fact that the core and the ring move at different speeds is one of the most surprising things that the spectral data showed. To find out how fast different parts of the galaxy are moving, scientists look at Doppler changes in the spectral lines, moving toward or away from us. In Hoag's object, the stars in the ring spin much faster than the stars in the core, and the two parts do not seem to be dynamically connected very well. This does not make sense. In most galaxies, the inner and outer parts are connected by a smooth change in wind speed. The sharp break in Hoag's object makes it seem like the ring and the core may have formed in very different ways. The difference in age between the two areas is another strange thing that spectroscopy has shown. Most of the stars in the ring are only a few billion years younger than the stars in the core. In fact, it looks like the ring has been through at least two separate bursts of star formation. One of them was fairly recent, maybe within the last billion years, and the other happened a lot longer ago. It is still not clear why a stable ring structure would turn on star creation so quickly, especially after the core had stopped working. The spectra also reveals something strange about the gas in the ring. Normally, the gas fueling star formation in a galaxy's outskirts either comes from the galaxy's own reservoir or it is captured from an intergalactic space. In both cases, the metallicity, the proportion of elements heavier than helium, follows a predictable pattern. But in Hoag's object, the metallicity gradient does not make sense. The ring's gas is chemically different from what you would expect if it had come from the core, yet it is also too enriched to have come directly from a pristine intergalactic gas. This mismatch deepens the mystery of where the ring's material came from. Some spectral traits are missing from both areas, which is weird. For example, the signs of shock-heated gas are weak or not present at all. This is common in galaxies that have collided or have had strong gravity interactions. This fits with the other proof that Hoag's object has not been through a violent event recently. However, it also takes away a big possibility for how the ring was formed in the first place. It is clear from these spectrum shocks that Hoag's object is more than just a strange thing to look at. It is also a chemical and a dynamical puzzle. Its old, quiet core and its younger star-forming ring are very different from each other. This goes against the usual evolutionary link between a galaxy's center and its edges. Like two different stories are being told at the same time, and no one is sure how they fit together. The infrared observations. A light that we can see can show us the big picture of a galaxy, but it does not always tell the whole story. Optical binoculars cannot always see things like dust, cooler stars, and secret areas where stars are forming. That is where the findings in infrared light come in. Astronomers can see through clouds of dust and find groups of cooler stars. They can also find traits that optical images miss totally by looking at longer wavelengths. When infrared light was shined on Hoag's object, it confirmed how strange it looked and added to the puzzle. The first surprise was the sheer lack of dust emission from the core. In most galaxies, even very old cores contain some dusty regions, either left over from past star formation or drifting in from the outer disk. The infrared wavelengths are especially good at picking up the glow of this warm dust. But in Hoag's object, the core appeared to be almost dust-free. This reinforces the optical impression of a pristine, untouched central region. If dust had been present at any point in the recent past, the infrared detectors would have lit up with its signature, but they did not. The ring, on the other hand, told a very different story. In the infrared images, it showed strong signals from both dust and the cooler, redder stars. This indicates that while the ring contains many young hot stars visible in optical light, it also hides an older population that has cooled enough to shine more brightly in infrared. This older component suggests that the ring has been around for much longer than a single starburst phase. This contradicts the idea that it might be a recent short-lived structure. The way that star-forming regions are spread out in the ring is another fascinating finding, a finding that the infrared data shows. The ring looks smooth in visible light with no big lumps that stand out, but in the infrared, scientists saw small changes in light that pointed to the places where new stars have heated up cooler dust. These tiny hotspots show a patchwork of activity that cannot be seen with optical wavelengths. This suggests that the past of star formation is more complicated than was thought before. The infrared studies also allowed astronomers to probe the metallicity of the hidden star populations. The older, cooler stars tend to have different spectral fingerprints in the infrared compared to younger stars. And by analyzing these patterns, scientists found that some parts of the ring have different chemical compositions. They differ significantly from the others. This hints at multiple episodes of gas inflow into the ring over time, each possibly from a different source. This would explain the patchy metallicity without invoking a major collision. A very strange discovery came from taking pictures of the empty space between the core and the ring. This was done with a deep infrared light. The infrared monitors should see almost nothing in the gap if it really did not have any stars in it. The gap did stay almost totally dark. This proved that it is not just an optical effect caused by dust blocking the light. Why is this important? The infrared pictures of other ring galaxies often show tiny bridges of stars in these kinds of gaps, but not in Hoag's object. This empty space is real and complete. The infrared data also shed light on the dynamics of the ring. By studying the motion of the cooler stars and dust clouds, astronomers confirmed that the ring is in a stable long-term orbit. It is not expanding like in collision-generated rings. This stability, combined with the presence of older stars in the ring, strengthens an idea. The idea that Hoag's object has maintained its peculiar configuration for billions of years. The optical telescopes had only barely picked up on this. But the infrared pictures showed a dim, long halo of scattered light beyond the ring. This halo might be the leftovers of an older, wider ring of stars, or it could be the mark of a dark matter distribution that goes far beyond the galaxy's visible parts. In either case, it is another piece in the puzzle of how such a well-balanced system could have grown and survived in such a cold place. The puzzle of Hoag's object was not solved by infrared studies, but they did show that the galaxy is even stranger than it appears to be in visible light. They strengthened the belief that this is not a typical ring galaxy. They did this by finding hidden stars, proving that the gap is really empty and showing a faint outer halo. It is possible that its story involves things or situations that we have not even started to think of yet. The problem with the stellar orbits. In most galaxies, we know a lot about the paths that stars take. In a spiral disk, an oval core, or an irregular system, gravity and mass spread cause stars to move in patterns. These patterns help astronomers guess how stars should move, and most of the time the measurements agree with the guesses. But in Hoag's object, the outer ring stars do not act the way that models say they should, and the changes are not small enough to ignore. The first sign of trouble came when astronomers measured the orbital speeds of the stars in the ring. They did this by using Doppler shifts. They found that while the star's velocities are broadly consistent with the galaxy's total mass, there are subtle deviations. Instead of following a perfectly flat rotation curve, the speeds dip and rise slightly at intervals along the ring. This is the kind expected if dark matter is smoothly distributed around the galaxy. This wobble is unusual for such a symmetrical structure. It implies that either the mass inside the ring is not evenly distributed, or something else is influencing the motion. The star's orbits seem to be very close together, which is another strange effect. In most galaxies, star paths are not all the same shape. Some are almost circular while others are longer. Over time, gravity pulls tend to spread out the stars, making this variety even greater. That being said, in Hoag's object's ring, the paths look like they are very spherical, like the stars have been locked into a nearly perfect loop. The standard models of how galaxies work do not easily explain this. How they can reach and keep that level of orbiting accuracy for billions of years without an outside influence. Simulations of ring galaxies show that such perfect orbits are often unstable over a cosmic timescale. Small perturbations from passing dwarf galaxies, uneven gas clouds, or even internal shifts should cause stars to drift slightly inward or outward. But in Hoag's object, there is no sign that this is happening. The ring has kept its narrow width, and the stars remain in place, as if they were held there by an invisible guide. Even the vertical motions of the stars do not fit neatly with the predictions. These are the tiny oscillations above and below the plane of the ring. In most galaxies, these oscillations gradually thicken a ring or a disk over time. In Hoag's object, the ring's thinness suggests that the vertical motions are suppressed more effectively than usual. This could mean that the dark matter halo surrounding the galaxy has an unusually smooth and symmetric shape. This would exert an even pull in all directions, but such a perfectly uniform halo would be rare, and it would need to match the core's mass distribution almost exactly. The gas in the ring does not match up with the star's paths in a unique manner. Even though the stars move in a pretty steady circle, some gas clouds move in or out slightly, and their speeds change in small ways that shouldn't be there if the ring were perfectly balanced. These differences show that the gas and stars are not reacting to the galaxy's gravity in the same way. This could be because of past events or ongoing small-scale flows of matter from outside the galaxy. The ring's steady orbit may be due to a resonance. This is when the periods of the star's orbits are in a simple numerical ratio with another spinning feature, a feature such as the core or a secret mass distribution. The stars can be shepherded into tight lanes by this type of resonance. This works a lot like the way the moons around our sun move planetary rings. The issue is that Hoag's object does not have any such shepherding feature, and the core moves too slowly to be the cause. The lack of orbital drift is especially puzzling when you consider the galaxy's age. If the ring has been in place for billions of years, it has survived countless potential disruptions. Things like passing intergalactic clouds, the gravitational pull of unseen small galaxies, and even the slow reshaping of its own halo. Yet the orbits remain pristine. This level of stability hints that either Hoag's object was formed in a remarkably undisturbed environment and has stayed that way, or that it is benefiting from some stabilizing mechanism that we have not yet discovered. A relic from the early universe. The galaxies do not last forever. Over billions of years they join, change, and grow. Many years of crashes, gas flows, and bursts of star formation have made most of the galaxies we see today, whether they are spirals, ellipticals, or irregulars. However, some scientists have thought, what if Hoag's object is different? If it is not the result of recent action but rather a fossil from a very long time ago, what would that mean? This idea stems from how unusual the galaxy structure is compared to its surroundings. Hoag's object sits in relative isolation far from the dense galaxy clusters where most merges happen. Its core is smooth, dust-free, and made up of older stars. These are features that hint at stability over billions of years. The ring, while containing younger stars now, could have been a part of the galaxy for most of its existence. With periodic star formation events triggered by slow, subtle processes rather than violent encounters, it is possible that Hoag's object was formed at a time when the world was very different from how it is now. In the early billion years after the Big Bang, galaxies were smaller and had more gas. They were also more likely to have bursts of star formation that happened very quickly. If Hoag's object had formed in a less busy part of space, it might not have been affected by chaotic merging, the merging that made other galaxies. It might have settled into its ring and core shape over time and stayed mostly the same. Support for this comes from the metallicity, the abundance of heavy elements in the galaxy's stars. The core's high metallicity suggests a long history of star formation that enriched the gas early on. This was followed by a sharp slowdown. The ring's metallicity, meanwhile, is consistent with a gas that has been processed over many billions of years, but not significantly disturbed. This is unlike younger ring galaxies, which often show signs of freshly captured, low metallicity material. If Hoag's object really is a relic, it could also explain its nearly perfect symmetry. Galaxies that have been dynamically stable for eons have time to relax into smoother, more regular shapes. The irregularities in the orbits of stars and gas get evened out over a cosmic timescale. This leads to the kind of geometric precision that we see in the ring. Any small distortions caused by minor gravitational nudges in the past could have been damped away. Long before humans ever looked through a telescope, this ancient origin theory, however, runs into a big question. How did it get the ring in the first place? The early universe was not known for producing such clean, large-scale rings without some sort of interaction. One idea is that Hoag's object could have started as a spiral galaxy. Its outer arms could have slowly evolved into a detached ring as gas flowed outward and settled into resonance orbits. Over billions of years, the spiral arms might have faded, leaving behind the isolated ring we see now. You could also think that Hoag's object is the leftovers of a very early gas-filled merger. But since it happened so long ago, all the trash that would have been a sign of it has been swallowed or spread out. In this case, the ring might have been made by gravity waves traveling through the galaxy's disk during the merger. The core, meanwhile, would have stayed together enough to keep its identity. The jumbled pieces from such an event would become invisible over time. This would make the galaxy look like it has not been affected by anything. Many people also think that the galaxy's dark matter ring may have helped to keep its old shape. If the halo is very dense, smooth, and circular, it might have acted as a gravity cushion, a cushion that kept the galaxy from being distorted by tides for billions of years. This could be the reason why the ring has not bent or broken, even though it looks very fragile. If Hoag's object is truly a relic from the early universe, then studying it could offer a rare window, a window into a bygone era of galactic evolution. Most galaxies that were formed back then have long since been reshaped beyond recognition, but Hoag's object may have escaped that fate. It could be a survivor from a time when the cosmic web was just starting to organize into the vast filaments and voids that we see today. This is still just a theory because there is no direct proof of its early past. No proof like very old stellar populations in the ring or traces of ancient gas chemistry. One thing that is certain is that if Hoag's object is a dinosaur galaxy, it has been a very well-preserved one, spinning slowly in perfect symmetry for a very long time. The statistical impossibility. In the universe, you can expect to find rare things. It is possible for strange alignments, extreme conditions, and odd forms to happen by chance in the world. But Hoag's object breaks that assumption to its limits. Astronomers have tried to figure out how likely it is that a galaxy would have certain features. A perfect ring, a perfect elliptical core, a big empty gap matching redshifts, stable dynamics, and perfect symmetry. The numbers get so small that they are almost ridiculous. To begin with, ring galaxies themselves are already rare. Only about 1 in 1,000 galaxies in the local universe shows a prominent ring, and most of those are the messy, collision-formed kind. Perfect smooth rings like Hoag's object are so uncommon that fewer than a dozen well-confirmed examples exist, and none of them match its size, its proportion, and its isolation. Then you factor in the size ratio between the ring and the core. In Hoag's object, the ring's diameter is roughly 4 times larger than the core's, and the empty gap is proportionally massive compared to other known systems. This alone places it in a category of 1. There is no other galaxy on record with such a large, clean separation. A separation between its central bulge and its outer ring without visible bridges of stars or dust. The symmetry adds another level of improbability. Cosmic structures are rarely perfect circles. Gravitational interactions, uneven star formation, and even random density fluctuations tend to warp them. For Hoag's object to maintain such a flawless geometry suggests either a unique stabilizing mechanism or a calm history, an almost impossibly calm history. In statistical terms, the odds of such a symmetry surviving over billions of years without disturbance are tiny, far smaller than the odds of a typical galaxy remaining undistorted for the same period. Then there is the age mismatch between the core and the ring. Most ring galaxies show either similar, stellar ages across both regions if they were formed together, or they show clear evidence of a recent event that rejuvenated one part. Hoag's object's stark difference means that whatever formed it had to not only create this arrangement, but also keep it intact. An ancient quiescent core surrounded by a still active ring, modeling the odds of that sequence of events only shrinks the probability further. If you treat each unusual feature of Hoag's object as an independent factor and multiply the probabilities, the result becomes very small. A perfect symmetry, a large gap, an old core with a young ring, an absence of debris, isolation, and stable orbits. The result becomes so small that it is hard to express in ordinary numbers. Even conservative estimates suggest the odds are far less than 1 in a billion for a galaxy to tick every one of these boxes. Some astronomers caution that multiplying probabilities like this can be misleading. This is because the features might not be entirely independent. For example, a particularly calm formation environment might increase the odds of both symmetry and stability at the same time. But even when allowing for these correlations, the odds remain shockingly low. It is as if the galaxy is playing by a different set of rules than the rest of the cosmos. The improbability has led some researchers to wonder if our surveys are missing other Hoag-like galaxies hidden in distant or poorly imaged regions. But so far, deeper sky scans have only reinforced its uniqueness. There are a handful of partial lookalikes galaxies with bright rings and faint centers, but none of them have the same proportions, emptiness, or undisturbed structure. Hoag's object is a warning to both statisticians and astronomers. A warning that the world sometimes has outliers so far out of the norm that they make the models themselves look wrong. Whatever theory you have about how galaxies form says something like, Hoag's object should almost never happen, but it does. The theory needs to be rethought. This statistical impossibility does not mean that the galaxy is magical or does not follow the rules of physics, but it does mean that there are things going on that we do not fully understand or have not seen happen anywhere else yet. Not only is Hoag's object possibly rare, it may also be the only example of a galaxy creation route that was more common in the past. This would make it both a time capsule and a statistical outlier. The Hubble's zoom-in mystery. When the Hubble Space Telescope turned its powerful optics towards Hoag's object in 2002, the goal was clear: to capture the most detailed image yet of its pristine ring and its golden core. What astronomers did not expect was to find something unusual hiding in plain sight. A tiny, faint galaxy was sitting inside the vast starless gap between the core and the ring. It is easy to miss the thing at first look. It is small, dim, and almost perfectly lined up with Hoag's object, like someone had put it there on purpose. It looks like a small spiral galaxy in the famous Hubble picture. Here it stands out as a long smudge in the middle of an otherwise empty space. This quickly made people wonder if it had anything to do with Hoag's object, or if it was just another cosmic chance. The discovery led to a flurry of speculation. If the small galaxy was gravitationally bound to Hoag's object, it could potentially offer clues about the ring's origin. For example, it might be a remnant core of another galaxy that once interacted with Hoag's object. It might have possibly triggered the formation of the ring, but if that were true, astronomers would expect to see some tidal debris, faint streams of stars or gas connecting the two. A careful imaging, however, revealed nothing of the sort. The gap between the small galaxy and the inner edge of the ring remains truly empty. Spectroscopic analysis provided the next big clue. By measuring the redshift of the small galaxy's light, astronomers determined its distance. It is not at the same distance as Hoag's object. Instead, it lies far behind it. This means it is just a background galaxy seen through the ring's inner void. This neatly explains why there is no sign of an interaction between the two, but it also makes the alignment seem incredibly coincidental. As a matter of fact, some scientists said that a few background galaxies will always be seen inside other galaxies. This is when it is seen from Earth. Space is very big, and the lines of sight cross over time. But for one to show up so exactly in the middle of Hoag's object's ring is strange. Especially in a galaxy so symmetrical and far away from everything else. Even experienced experts find it strange. The background galaxy's shape also sparked a curiosity. It appears to be a barred spiral, a type of galaxy with a central bar of stars and two sweeping arms. It is seen almost face-on. This means that its round shape in the image mirrors the circular geometry of Hoag's object's ring. This makes the alignment all the more striking. To the casual observer, it might look like a galaxy within a galaxy, even though they are separated by vast distances. Hubble's zoom-in on the core and gap region not only revealed this background galaxy, it also allowed astronomers to confirm just how clean the empty space between the core and ring truly is. Even in Hubble's incredible resolution, no faint star clusters, gas clouds, or dust lanes fill the gap. This absence reinforces the idea that the ring and core are dynamically and structurally separate. They have no material linking them, a fact that continues to challenge formation theories. Since then, the tiny galaxy in the gap has become a popular thing to talk about when Hubble's pictures are shown. For the public, it makes the sky even stranger by adding a silly cosmic bullseye feature to it. For scientists, it is a warning that the universe is three-dimensional and that redshift readings are important for telling the difference between real connections and optical illusions. The background galaxy does not explain Hoag's object and does not seem to have anything to do with its structure, but the fact that it exists shows how optical positions in space can be so accurate that they almost look like they were planned. It kind of adds to the improbability of Hoag's object, as if one of the strangest galaxies ever found needed a small, strange thing hidden in the middle of it. Needed to make things even stranger, The problem with tidal forces. Studying tidal forces is one of the easiest ways for scientists to see if a galaxy's structure can last for billions of years. These are the stretching and pulling caused by gravity from other nearby large objects. These forces are a big part of how most ring galaxies change shape, twist, or lose their unity over time. But Hoag's object does not seem to follow these rules. Even though it has a thin, separated ring and a huge, empty space between them, it does not seem to be bent or stretched. It is not disturbed by the pulls of gravity from its surroundings. Normally, galaxies are never truly alone. Even in seemingly empty parts of the universe, they are part of larger gravitational networks. Networks that include dwarf companions, nearby spirals or ellipticals, and the overarching pull of galaxy groups. These neighbors, whether close or tens of millions of light-years away, exert tidal forces that can subtly distort shapes over time. Rings can become oval, spiral, arms can twist, and cores can become lopsided. The more fragile a structure is, the more quickly tidal forces can leave their mark. Hoag's object, however, sits in near-perfect isolation. Surveys of the region around it have found no large galaxies within a threatening range, and even small companions are rare. This extreme solitude means that tidal forces from outside are already weaker than average. But isolation alone does not explain everything. This is because, even without nearby galaxies, the cosmic web itself exerts a diffuse but measurable tidal influence. In most simulations, a galaxy with such a large and empty inner gap should be more vulnerable to these subtle forces. With so little material between the core and the ring to stabilize the gravitational field, the outer ring ought to be more easily perturbed. Over hundreds of millions of years, it could be expected to drift inward, to warp slightly, or even to fragment into clumps. Yet, observations show that the ring's shape is as perfect as ever. It has no detectable warping or asymmetry. There is another layer to the puzzle: the interaction between the core's gravity and the ring's mass. In many galaxies, the stars and gas in a ring interact gravitationally with the central bulge. This leads to complex orbital patterns. If the balance is not perfect, tidal stresses from the core itself can cause parts of the ring to spread outward or collapse inward. For Hoag's object, the balance seems uncannily precise. It's as if the core and the ring have been locked in a long-term gravitational truce. This stability raises the possibility that the galaxy's dark matter halo is playing a key role. If the halo is unusually smooth, spherical, and evenly distributed, it could create a perfectly symmetrical gravitational environment, an environment that shields the ring from tidal distortion. Such a halo would essentially wrap the galaxy in a protective bubble. It would keep the ring's orbit stable despite the lack of material in the gap. However, halos that are this uniform are thought to be rare. This makes Hoag's object even more of an outlier. The lack of tidal disruption also challenges the idea that Hoag's object is the result of a past collision. If it had formed from an interaction with another galaxy, the tidal forces from that event should have left some lasting imprint. A faint trail of stars, an off-center core, or an uneven density in the ring. The total absence of these features suggests that if a collision did occur, it must have been so long ago, or it was so gentle that all traces have been erased, a scenario that is itself statistically unlikely. Astronomers often find that tidal forces should have changed the shape of Hoag's object over a cosmic timescale. That is, if it was not for some kind of ongoing sustaining force. These changes have not happened in real life. This means that either important parts of physics are missing from the models, or Hoag's object is in a very rare gravitational sweet spot, a hidden mass discrepancy. It is not as easy as adding up all of the stars we can see to figure out how heavy a galaxy is. The vast majority of a galaxy's mass is hidden from view, either in dark matter or in gas and dust that do not look bright to the naked eye. Scientists can tell a galaxy's total mass by how fast its stars and gas are moving. The difference between this mass and the mass of the visible matter is usually big, but it is expected. That is not what Hoag's object does. The difference between what we think its mass is and what we see as its light is so strange. It makes us wonder if we are even measuring it right. The starting point for a mass measurement is the galaxy's rotation curve, a plot of how fast stars and gas move at different distances from the center. In most galaxies, rotation speeds stay high even far from the core. This suggests the presence of a large dark matter halo. For Hoag's object, the speeds in the ring are consistent with there being plenty of extra mass that is beyond what is visible. However, when astronomers estimate the mass of the stars and gas, we can see the numbers do not quite line up. They don't line up with the expected ratio. Hoag's object seems to have more total mass than the brightness of its stars suggests, but it also has less dark matter than would normally be required to hold such a large, thin ring together. This puts it in a strange middle zone, a zone where neither a standard dark matter model nor a purely baryonic explanation fits cleanly. Many of the galaxy's missing visible mass might be stuck in dim, low-mass stars. According to one theory, if these stars are old and bright, they give off very little light. This makes them hard to find. If there are a lot of these faint stars in the ring, along with its younger, brighter stars, they could make the galaxy heavier without making it brighter overall. Studies that use infrared light have given us hints about this secret community, but not enough to completely fill in the blanks. It is also viable that the galaxy has a lot of cold gas that does not give off much light, not at the wavelengths usually used to test hydrogen content. The 21 centimeter radio line is generally used to find neutral hydrogen, but the gas might not be picked up if it is very cold or is stuck in a molecular form. This dark gas might be adding to the galaxy's pull on us, even though it does not show up in regular measurements. Some researchers have also considered whether the dark matter halo of Hoag's object might be shaped differently from the halos in other galaxies. If the halo is more concentrated toward the ring rather than spread evenly around the galaxy, it could account for the ring's stability. It could do this without requiring as much total dark matter. Such a configuration, however, is rarely seen in simulations, which tend to produce smoother halos less influenced by very specific formation events. The hidden mass problem becomes even stranger when you account for the galaxy's isolation. Without nearby galaxies to steal or to share mass with Hoag's object's mass distribution should be relatively straightforward. Yet the measurements continue to resist a neat classification. Some teams have suggested that our standard assumptions about the relationship between light and mass might simply not apply here. That the processes that formed Hoag's object gave it a fundamentally different mass-to-light ratio, different than most galaxies. This could mean that Hoag's object is more than just a strange structure, if it is true. It could also mean that our models of how galaxies form are missing an important variable. This is especially true when it comes to how mass is spread between stars, gas, and dark matter. It is possible that galaxies can form with dark matter halos that lock in matter in strange ways, creating the stable symmetric rings that we see here. Could it be transient? A galaxy's time is not frozen. It could be millions or billions of years, but their forms, structures, and star populations change over time. Some shapes, like classic spirals or giant ellipticals, are pretty stable. They stay the same for very long periods of time in the universe. Others are temporary and can only be seen for a short time before they are changed by gravity. This makes me wonder if Hoag's object is one of these short-lived phases, a brief arrangement in the universe that was caught at just the right time. The idea comes from the fact that Hoag's object's ring might not be able to keep its shape forever. Even though it seems to be fixed right now, Computer models of ring galaxies often show that the ring moves inward or spreads out over time, especially the ones where the core and ring do not seem to be connected. If the stars in Hoag's object's ring move slowly toward the gap or out into space, the ring might lose its perfect balance. If that is true, then we might be seeing the galaxy during a sweet spot in its evolution, long enough after its formation for the ring to settle into its clean shape, but before the forces that disrupt such structures have fully taken hold. This window might last only a few 100 million years, a blink compared to the galaxy's total age. This would make catching it now a stroke of astronomical luck. Using a form of the transient theory, the ring could be a wave left over from a disturbance that happened a long time ago. Something caused a gravity ripple that pushed gas and stars outward in a circle, maybe a small galaxy or a burst of star formation inside the galaxy. The wave would get smaller over time, the ring would lose its shape, and the stars would spread out. If Hoag's object is in the middle of that process, we might be seeing a phase that will soon end. The galaxy might also be briefly taking in gas from its surroundings. If a thin, long cloud of gas fell toward Hoag's object in the past, it could have been caught in a stable orbit, an orbit that is now helping new stars to form in the ring. That gas will run out eventually, the birth of new stars will slow down, and the ring will become less bright, so it will not stand out as a perfect halo. The transient idea also connects to the age difference between the core and the ring. If the ring stars are relatively young compared to the core, then this current configuration cannot have been in place for the entire history. The galaxy's entire history. That means the ring either was formed recently or was rejuvenated by a fresh influx of material. In either case, the clock would already be ticking for how long it will remain in its present form. What makes this theory compelling is that many of the features that make Hoag's object so strange might simply be side effects. The sharp separation between the ring and the core, the absence of connecting structures, the perfect symmetry. Side effects of catching it during this rare, short-lived stage. If we came back in 1 billion years, it might look completely different, with the ring dispersed into a faint haze or drawn inward toward the core. On the other hand, the transient explanation faces its own challenges. For one, the ring's stability appears to be unusually high for something that is supposed to be temporary. Measurements of the star's motions suggest that the ring is not in immediate danger of falling apart. This means the short-lived window might not be as short as this theory requires. Moreover, no clear evidence of the triggering event has been found. No leftover debris or distorted gas clouds. We are very fortunate to be able to see Hoag's object right now, if it is indeed temporary. It also means that there may be other galaxies like it, but at any given time only a few of them would be visible in this phase. This could be why scientists have not found many close matches. There are not many chances to find one at the right time. Why Hoag's object still has no consensus. Over time, puzzles in science tend to get less mysterious. Objects that were once hard to explain generally fit into existing theories as tools get better, as models get better and measurements get more accurate. But that trend has not been followed by Hoag's object. It is still one of the most debated galaxies, even after decades of research. This is not because we do not have enough information. It is because the information does not fit nicely into any one theory. The problem is not that scientists have no theories. In fact, they have several collision models, resonance wave models, ancient relic scenarios, and even rare dark matter configurations. The issue is that every theory explains some features of Hoag's object while contradicting others. The collision idea can explain the separation between the core and the ring, but not the total lack of debris. The resonance models can explain the symmetry, but they struggle to account for the age difference. The relic from the early universe theory works for the core's properties, but not for the ring's ongoing star formation. This partial fit problem has led to a kind of scientific stalemate. Teams often pick the model that they find most promising. They adjust it to explain one or two of Hoag's object's strangest traits, and they end up with a result that still leaves unanswered questions. The galaxy has essentially become a stress test for formation theories. If your model can explain Hoag's object in full, then it is probably robust enough to explain almost anything. So far, no model has passed. Not only is Hoag's object alone, but it is also very hard. Astronomers could look for trends and shared histories by comparing dozens of very similar galaxies, but the real things that look like Hoag are so uncommon that we cannot make a mathematical picture. Every time scientists think they have found a galaxy like ours, a closer look shows it is not quite the same. For example, the ring might be curved, the core might be off, or the gap might be full of faint junk. Technology has helped us to learn more about Hoag's object, but it has not delivered the knockout evidence needed to end the debate. Hubble's high-resolution images in 2002 showed the galaxy in stunning detail, but they also deepened the mystery by confirming its near-perfect symmetry and its emptiness. The radio and infrared surveys have given us clues about its gas content and its hidden stars. Yet none of these findings have been decisive enough to crown a single theory as correct. It is not just a technical problem that there is not an agreement. It is also a moral one. Astronomers are used to working within theories that explain most galaxies as the result of common cosmic processes. Processes such as gravity merging, galaxies, accretion, and cycles of star formation. The unique features of Hoag's object make us think something is missing. Either we are missing a rare but normal way for galaxies to form, or we need to rethink how adaptable our galaxy models are. Neither result makes you feel good. Some experts think that the answer might be somewhere that cannot be seen. The extreme ultraviolet X-rays or even gravitational waves could be used to see more about how the galaxy has changed, or to find patterns in its dark matter ring that have been hidden. Others think that the next generation of telescopes will be able to pick up on very faint objects. Telescopes like the Extremely Large Telescope or the Nancy Grace Roman Space Telescope. Or they will pick up small changes that could help us to figure out where they came from. For now, Hoag's object remains a case study in scientific patience. It is a reminder that not all puzzles can be solved quickly, even in an age of rapid technological advancement. The galaxy floats in its cosmic isolation, seemingly aware that it is the subject of decades-long arguments among Earth's astronomers, and offering no new hints to break the tie. For now, Hoag's object is still a case study in science patience. It serves as a warning that even in this age of fast technological progress, not all puzzles can be solved right away. As it floats in space by itself, the galaxy seems to be aware of the decades-long arguments, aware that it has been the subject of these arguments among scientists on Earth. But it does not offer any new information to break the tie. And so Hoag's object remains out there, a lonely perfect ring in the vast dark, daring us to explain it and defying every answer that we come up with. Maybe one day we will crack its code, or maybe it is the universe's way of reminding us that some mysteries are meant to last.